For centuries, humanity has dreamed of unlocking a limitless source of power, an energy so vast, so clean, and so unstoppable that it could fuel our entire planet forever. We've tried coal, oil, wind, solar, and even nuclear fission. Each brought us a step closer, but none held the ultimate key. Now, after decades of searching, science may be standing at the brink of a breakthrough so powerful it could rewrite the future of civilization. Imagine a world where energy bills vanish, where pollution becomes a thing of the past, and where progress is no longer chained by scarcity. What is it? How close are we? And what happens when we finally crack the code? Let's dive into the concept of infinite energy and uncover its potential impact on humanity. Energy is the driving force behind nearly everything in our world. It powers our homes, fuels our transportation, and drives industrial progress. For centuries, we have relied on limited sources of energy, such as coal, oil, natural gas, and nuclear power. But imagine a world where energy is limitless, available at all times, and completely free from the environmental damage caused by current energy sources. This idea is what scientists and researchers are aiming for when they talk about infinite energy. Infinite energy is the concept of having an inexhaustible supply of energy, one that does not run out no matter how much we use. It refers to energy that can be generated continuously without depleting any resources or harming the planet. This kind of energy would not be limited by time, space, or any physical constraints. In a sense, it would be a form of energy that could last forever, meeting the ever-growing demand for power and improving the quality of life for every person on Earth. Infinite energy, as the name suggests, is energy that is limitless. Unlike traditional energy sources that rely on finite resources, such as fossil fuels or uranium, infinite energy does not run out. This kind of energy can be produced endlessly without any significant environmental cost, and it would allow us to meet the world's growing energy needs without worrying about running out of resources or causing pollution. To understand this concept better, think about the sources of energy we currently rely on. Fossil fuels like coal, oil, and natural gas are formed from ancient plants and animals that took millions of years to create. Once we burn them for energy, we are using up resources that took eons to form, and when they're gone, they're gone. This is not the case with infinite energy. Instead of relying on a finite resource, infinite energy would be generated in a way that could continue forever. The concept of infinite energy often brings to mind ideas like perpetual motion machines or harnessing the power of the universe itself. These ideas sound like science fiction, but scientists have been exploring ways to create sustainable energy for many years. While we are far from discovering a truly infinite energy source, research into clean, renewable, and near-infinite forms of energy has made significant progress. The potential for infinite energy is revolutionary because it would completely change how we live. Today, much of the world's energy comes from burning fossil fuels, which causes environmental destruction, including air pollution, global warming, and damage to ecosystems. If we could generate energy that was completely clean and limitless, we could eliminate many of the issues we face today. Let's explore the reasons why infinite energy is so revolutionary. One of the most pressing concerns of our time is climate change. The burning of fossil fuels is a major contributor to global warming, leading to rising temperatures, extreme weather events, and environmental damage. Coal, oil, and natural gas release harmful gases, such as carbon dioxide, into the atmosphere when burned, contributing to the greenhouse effect. These gases trap heat and cause the Earth's temperature to rise, resulting in melting ice caps, rising sea levels, and loss of biodiversity. If we could tap into infinite energy, we would no longer need to rely on these damaging sources of power. Infinite energy would be a clean, renewable energy source that does not produce harmful emissions. By switching to this type of energy, we could drastically reduce pollution and help slow down the process of climate change. This could lead to cleaner air, healthier ecosystems, and a more stable global climate. In many parts of the world, access to reliable and affordable energy is a major challenge. Some people live in areas where electricity is scarce, and they rely on expensive or dangerous methods of generating power, such as burning wood or kerosene. Infinite energy could change this by making energy available to everyone, everywhere. If infinite energy sources were developed, they could be used to provide affordable electricity to remote or impoverished areas. This would help to lift millions of people out of poverty by providing them with the power they need for education, healthcare, and economic development. For example, schools could have reliable electricity to power computers and lights, and hospitals could run medical equipment without worrying about power outages. Furthermore, the availability of infinite energy could reduce the reliance on expensive energy imports, especially for countries that do not have their own natural energy resources. Countries could become self-sufficient in their energy needs, leading to greater energy security and economic stability. Currently, the cost of energy is a major concern for both consumers and businesses. The prices of electricity, fuel, and gas fluctuate depending on global market conditions, supply chains, and geopolitical factors. As a result, people and companies often face unpredictable energy costs, which can make it difficult to plan for the future. Infinite energy would revolutionize the cost structure of energy. If energy could be generated for free or at a minimal cost, it would drastically reduce the financial burden on consumers. Imagine paying little to no monthly electricity bills or fueling your car with a clean and limitless energy source. This would also benefit businesses by lowering operational costs and encouraging innovation. For governments, reducing energy costs could also ease the pressure on public services. Instead of spending billions on energy imports or subsidies for fossil fuels, governments could invest in clean energy infrastructure and social programs. The overall cost of living could decrease, and economies could grow more efficiently. Infinite energy could also drive technological innovation. With an abundant and reliable energy source, we could develop new technologies that were previously unthinkable. For instance, energy-intensive industries like space exploration, artificial intelligence, and large-scale manufacturing could flourish. These fields could advance at a much faster rate with access to virtually unlimited power. One of the most exciting possibilities is the potential for clean, renewable energy to be used in space exploration. With infinite energy, we could launch spacecraft that never run out of fuel, and we could set up permanent bases on the Moon or Mars. We could also send probes deeper into space, exploring distant planets and stars. Infinite energy could make humanity a multi-planetary species, helping us expand our reach into the universe. Furthermore, infinite energy could enable breakthroughs in healthcare, transportation, and communication. For example, medical research could be conducted more efficiently with unlimited energy, leading to faster discoveries of cures for diseases. In transportation, electric vehicles could become more widespread, reducing dependence on fossil fuels and cutting down on emissions. In communication, new technologies could emerge, making global connectivity faster and more reliable. While the idea of infinite energy is revolutionary, the practicalities of achieving it are much more complicated. Scientists and engineers are exploring several methods of generating energy that could come close to being infinite. Some of these ideas are already being researched, while others remain theoretical. Let's look at some of the most promising avenues for creating infinite energy. Nuclear fusion is often considered the holy grail of energy generation. Fusion is the process that powers the Sun and other stars. It involves fusing two light atomic nuclei, such as hydrogen, to create a heavier nucleus, releasing vast amounts of energy in the process. If we could replicate fusion here on Earth, we could have an almost limitless supply of energy, as hydrogen is abundant and readily available. The problem with fusion, however, is that it is incredibly difficult to achieve. The conditions required for fusion, extremely high temperatures and pressures, are challenging to recreate in a controlled environment. For decades, scientists have been working on experimental fusion reactors, and while progress has been made, we are still far from achieving commercial fusion power. However, if successful, fusion energy could provide a nearly unlimited and clean energy source for the world. Geothermal energy is another form of renewable energy that could potentially be harnessed indefinitely. It involves tapping into the heat from the Earth's core, which is constantly replenished by natural processes. This heat can be used to generate electricity or provide heating for buildings. In some regions of the world, such as Iceland and parts of the United States, geothermal energy is already being used successfully. While geothermal energy is not truly infinite, it is a long-lasting and sustainable resource that can be harnessed for thousands of years. Expanding geothermal energy production could help reduce reliance on fossil fuels and provide clean, renewable energy for millions of people. Solar power is one of the most promising renewable energy sources available today. The sun produces an enormous amount of energy, and by capturing sunlight using solar panels, we can convert it into electricity. Solar energy is abundant and free, and as technology improves, solar panels are becoming more efficient and affordable. While solar power is not technically infinite, the energy it provides is effectively limitless, as the sun will continue to shine for billions of years. By building large-scale solar farms and improving energy storage technologies, we could make solar power a key player in meeting the world's energy needs. In addition to these practical approaches, there are several theoretical concepts that could potentially provide infinite energy. For example, scientists have proposed the idea of harnessing the energy from black holes, tapping into the quantum fluctuations of space-time, or even using dark matter and dark energy. While these ideas are fascinating and could revolutionize energy production, they remain speculative and far beyond our current technological capabilities. When we talk about finite resources, we are talking about things that are limited, that will run out if we keep using them. Fossil fuels like coal, oil, and natural gas are examples of finite energy sources. These fuels were created over millions of years, and once used up, they cannot be replaced on a human timescale. This is because they are formed from the remains of ancient plants and animals, and it takes geological processes millions of years to create them. On the other hand, infinite energy refers to energy sources that will not run out, at least not in any foreseeable future. These sources are typically natural forces that are constantly available and can be harnessed for human use. The most famous infinite energy sources are solar power, wind power, and hydroelectric power. These energy sources are all driven by natural processes that happen continuously. Before we dive into what makes energy infinite, let's take a closer look at fossil fuels and why they are considered finite. Fossil fuels were formed millions of years ago from the remains of plants and animals that lived in ancient forests, swamps, and oceans. Over time, the remains of these organisms were buried under layers of dirt and rock. The heat and pressure from these layers eventually turned the organic material into coal, oil, and natural gas. Fossil fuels have powered much of the world's energy needs for the past few centuries. They are used to produce electricity, heat homes, fuel vehicles, and power industrial machinery. However, fossil fuels are not only finite, they also have serious environmental impacts. Burning fossil fuels releases carbon dioxide and other harmful gases into the atmosphere, contributing to global warming and air pollution. One of the major problems with fossil fuels is that they are not evenly distributed around the world. Some countries have abundant reserves of oil and natural gas, while others have very little. This has led to geopolitical conflicts and struggles over access to these resources. Furthermore, extracting and burning fossil fuels also comes with environmental costs, such as oil spills, air pollution, and habitat destruction. Fossil fuels are running out. Experts have warned for decades that the world's supplies of easily accessible oil, coal, and natural gas are shrinking. As we continue to use fossil fuels at a rapid pace, the cost of extracting them increases and the environmental damage grows. This is why many experts agree that it is essential to find alternative energy sources that are more sustainable. In contrast to fossil fuels, infinite energy sources do not have these limitations. These sources are renewable, meaning they can be replenished naturally and are not subject to exhaustion in the same way that fossil fuels are. Let's explore some of the most important infinite energy sources. Solar power is one of the most well-known forms of infinite energy. The sun produces an incredible amount of energy, and this energy is constantly reaching the Earth. In fact, the Earth receives more energy from the sun in 1 hour than the entire world uses in 1 year. This makes solar power an incredibly abundant and renewable resource. Solar panels are used to capture the sun's energy and convert it into electricity. These panels are made up of photovoltaic cells, which convert sunlight directly into electricity. Solar power can be harnessed anywhere in the world as long as there is sunlight. This makes it an ideal source of energy for many regions, especially those that are not connected to a larger electrical grid. One of the major advantages of solar power is that it is free once the solar panels are installed. The sun will continue to shine for billions of years, so there is no risk of running out of solar energy. Furthermore, solar power is clean, meaning it does not produce harmful emissions or contribute to air pollution. However, there are challenges to using solar power. For example, solar panels require sunlight to generate electricity, which means they are less effective at night or in cloudy regions. Storage technology, like batteries, is being developed to store excess energy generated during the day for use at night or during cloudy weather. Wind power is another form of infinite energy. Wind is caused by the movement of air masses due to differences in temperature and pressure around the Earth. As long as the Earth's atmosphere exists, wind will continue to blow, making wind power a renewable and limitless resource. Wind turbines are used to capture the energy of the wind and convert it into electricity. These turbines are typically placed in areas with consistent and strong winds, such as coastal regions, plains, and mountain passes. Wind farms, which are groups of wind turbines, can generate large amounts of electricity to power homes, businesses, and industries. Like solar power, wind power is a clean and renewable energy source. It does not produce greenhouse gases or contribute to climate change. Wind power also has the advantage of being scalable, meaning that small wind turbines can be used for individual homes, or large wind farms can generate electricity for entire cities. However, wind power also has challenges. Wind turbines are dependent on the availability of wind, so they are less effective on calm days or in areas with weak winds. There are also concerns about the impact of wind farms on wildlife, particularly birds and bats, although studies have shown that these impacts are relatively small compared to the environmental damage caused by fossil fuels. Hydroelectric power, or hydropower, is another form of infinite energy. It uses the energy of flowing water to generate electricity. Hydroelectric power plants are typically built on rivers or dams, where the movement of water is harnessed to turn turbines, which then generate electricity. The energy from moving water is essentially limitless as long as the water cycle continues. Water is constantly moving through the Earth's rivers, lakes, and oceans due to the forces of gravity and evaporation. This makes hydroelectric power a reliable and sustainable source of energy. Hydroelectric power has been used for centuries, and it is still one of the largest sources of renewable energy in the world. In fact, about 20% of the world's electricity comes from hydroelectric power. It has the advantage of being highly efficient, and large-scale hydroelectric plants can generate massive amounts of electricity. However, hydroelectric power is not without its challenges. Building dams and large-scale hydro plants can be expensive, and they can disrupt ecosystems and wildlife habitats. In some cases, dams have caused the flooding of entire areas. displacing people and animals. There is also the issue of droughts and changes in rainfall patterns, which can affect the availability of water for hydroelectric plants. Infinite energy sources like solar, wind, and hydropower have many advantages over fossil fuels. First, they are renewable. As long as the sun shines, the wind blows, and water flows, these energy sources will be available. This means we won't run out of them, unlike fossil fuels, which are limited and will eventually be depleted. Furthermore, infinite energy sources are much cleaner than fossil fuels. Burning fossil fuels releases harmful pollutants into the air and contributes to climate change. In contrast, solar, wind, and hydropower do not produce carbon emissions or other pollutants. This makes them essential in the fight against global warming and air pollution. Additionally, infinite energy sources can help reduce our dependence on fossil fuels. By using more renewable energy, we can reduce the amount of coal, oil, and gas we need to extract and burn. This can help reduce the environmental damage caused by mining and drilling, as well as decrease the geopolitical tensions related to fossil fuel resources. Infinite energy sources are often cheaper in the long run. While installing solar panels or wind turbines can require a significant upfront investment, the ongoing costs are much lower compared to the cost of fossil fuels. Once a solar panel or wind turbine is installed, it can generate electricity for many years without the need for expensive fuel. Nuclear fusion is an incredible process where two or more tiny particles at the heart of atoms, called atomic nuclei, come together to form a larger, heavier nucleus. When this happens, a small amount of the mass of the original particles disappears and turns into energy. This happens because of differences in the energy that holds the atomic nuclei together before and after the fusion. This energy is either released or absorbed, depending on the type of reaction. Fusion is the powerful force that makes all stars in the universe shine, including our very own sun. Stars get their energy from various fusion reactions happening deep inside their cores. But fusion doesn't happen easily. It needs extremely high temperatures, very high pressure, and enough time to keep the reacting particles close together. This combination is known as the triple product. These extreme conditions are only found naturally in the centers of stars or during the explosions of advanced nuclear weapons. Scientists are trying to create these conditions in laboratories and fusion power plants, but it's still very difficult. When fusion creates elements lighter than nickel-62, it usually gives off energy. This is because lighter elements have less tightly bound nuclei, so when they join, extra energy is released. The easiest atoms to fuse are among the lightest, like deuterium, a form of hydrogen with one neutron, tritium, hydrogen with two neutrons, and helium-3. On the other hand, nuclear fission, the opposite process, breaks apart very heavy nuclei like uranium or plutonium and also releases a lot of energy. Fusion has several uses. It powers stars, fuels thermonuclear, hydrogen bombs, boosts regular nuclear bombs, helps create neutron sources for experiments, and is even used to create super-heavy elements in laboratories. The idea of fusion was first proposed in the year 1915 by an American chemist named William Draper Harkins. Just 4 years later, in 1919, Francis William Aston invented the mass spectrometer, which helped him discover that 4 hydrogen atoms weighed more than 1 helium atom. This hinted that when hydrogen atoms fuse into helium, some mass turns into energy. In the year 1920, British astronomer Arthur Eddington predicted correctly that this fusion process is what powers the stars. In the late 1920s, German physicist Friedrich Hund discovered quantum tunneling, a strange effect that allows tiny particles to pass through barriers they normally couldn't. In 1928, Russian scientist George Gamow applied this idea to atomic nuclei, first explaining alpha decay, a type of radioactive decay, and then fusion. Inspired by Gamow's work, Robert Atkinson and Fritz Houtemans in 1929 estimated how often fusion reactions might happen inside stars. By the year 1938, Hans Bethe and Charles Critchfield described the proton-proton chain reaction, which is the main way stars like the Sun produce energy. 1 year later, Bethe explained another process called the CNO cycle, common in bigger stars. During the 1920s, Patrick Blackett did the first solid experiments in changing one element into another using artificial nuclear reactions. Around the same time, scientists John Cockcroft and Ernest Walton built a machine inspired by Gamow's work. In April of 1932, they carried out one of the first artificial fusion reactions using hydrogen and lithium. They briefly created a form of beryllium that existed for only a tiny moment. In the early 1930s, researchers at the University of California accidentally caused fusion between two deuterium atoms during cyclotron experiments. They thought it was just the deuterium falling apart, but later it was understood to be fusion. Then, in May of 1934, Mark Oliphant, Paul Hartek, and Ernest Rutherford intentionally caused deuterium to fuse, discovering both tritium and helium-3 in the process. This is now seen as the first real proof of fusion in a lab. In 1938, Arthur Rulig at the University of Michigan first noticed the fusion between deuterium and tritium. This reaction gave off powerful neutrons with an energy of about 14 million electron volts, and it's now known as one of the best fusion reactions to produce energy. During the early 1940s, fusion became a topic of military interest as part of the Manhattan Project, the top-secret US program to develop nuclear weapons. In 1941, scientists Enrico Fermi and Edward Teller discussed using a fission bomb to create conditions for fusion. The following year, physicist Emil Konopinski brought Arthur Rulig's fusion research to the project's attention. J. Robert Oppenheimer assigned researchers to quietly study how likely fusion was to occur. These studies happened between the years 1942 and 1946. At first, they believed deuterium-deuterium and deuterium-tritium reactions would behave similarly. But in 1946, Egon Bretscher discovered that the deuterium-tritium reaction had a much higher chance, about 100 times greater, of happening thanks to something called a resonance effect. Starting in 1945, scientists at Los Alamos used one of the world's first computers, ENIAC, to simulate fusion explosions for hydrogen bomb designs. The first successful artificial thermonuclear fusion explosion happened in 1951 during the US Greenhouse George nuclear test. It used a small amount of deuterium-tritium gas and produced a blast 225,000 tons strong, 15 times more powerful than the atomic bomb dropped on Hiroshima. The first true hydrogen bomb, using a two-stage design, was tested in 1952 in the Ivy Mike experiment. It used liquid deuterium and produced a massive explosion of over 10 million tons of TNT. This was made possible by the Teller-Ulam design, which used a fission explosion to trigger fusion more effectively. The Soviet Union was also working on hydrogen bombs. In 1953, they tested the RDS-6, the first fusion bomb that could be dropped from an airplane with a blast of 400,000 tons. Then, in 1955, they tested RDS-37, a two-stage fusion bomb with a yield of 1.5 million tons, also based on their version of the Teller-Ulam idea. Modern hydrogen bombs use a solid material called lithium deuteride, enriched with a special form of lithium named lithium-6. During the explosion, this creates tritium and sets off the powerful deuterium-tritium reaction. The reaction also produces lots of neutrons, which help keep the chain going. Although hydrogen bombs were once considered for generating electricity, peaceful uses of fusion have always focused on controlled reactions. Scientists have been working to create safe and steady fusion power since the 1930s. In 1958, a machine called Scylla the Frun at Los Alamos National Laboratory made the first fusion in a laboratory setting. Still, fusion power remains a work in progress, but researchers around the world are getting closer every year. In the United States, there's a special research center called the National Ignition Facility, or NIF for short. This facility uses a powerful method known as inertial confinement fusion, where lasers are used to squeeze and heat fuel until it fuses. The main goal of this project was to reach a point where the fusion reaction produces more energy than what was put in to start it. This is called achieving an energy gain factor greater than 1, also known as break-even. The first major experiments using this technique began in June of 2009, and more serious tests aiming to create fusion started in early 2011. Then, something truly historic happened. On December 5, 2022, the team at NIF finally reached break-even fusion. They shot lasers delivering 2.05 megajoules of energy into a fuel target and got back 3.15 megajoules of energy from the fusion reaction. Just over a week later, on December 13th, the US Department of Energy proudly announced this huge milestone to the world. Before this success, scientists had never managed to create a controlled fusion reaction that produced more energy than it consumed. There are two main ways scientists try to do this: magnetic confinement, using donut-shaped reactors called tokamaks, and inertial confinement, which uses lasers like at NIF. A large international project called ITER, short for International Thermonuclear Experimental Reactor, is currently being built using the magnetic method. It's designed to eventually create 10 times more fusion energy than the energy it uses to heat its plasma fuel. ITER is expected to complete its construction in 2025, begin testing and commissioning that same year, and start using deuterium-tritium fuel for real fusion reactions by 2035. Fusion energy is no longer just a government project. In 2021, private companies raised an impressive $2.6 billion from investors, hoping to make fusion a real energy source for the world. Some of the big names in this race include Commonwealth Fusion Systems, Helion Energy, General Fusion, TAE Technologies, and ZAP Energy. One exciting development happened in France, where a reactor called West kept a superhot plasma at a temperature of 90 million degrees, going for 6 full minutes. This set a record and showed progress in the same type of fusion machine that ITER will use, the tokamak design. Fusion is all about smashing small atoms together so hard that they join to form a larger atom, and when this happens, a huge amount of energy is released. But this isn't easy. Nuclei, which are the centers of atoms, contain positively charged protons, and these naturally push away from each other because of something called the Coulomb force. However, there's also the nuclear force, a strong but very short-range attraction that pulls protons and neutrons together. For small, light atoms like hydrogen or helium, the nuclear force can overpower the repulsion and allow them to fuse. When this happens, the new nucleus formed has less mass than the two original ones combined. The missing mass is released as energy. But this only works for lighter atoms. When scientists try to fuse larger, heavier atoms, the nuclear force isn't strong enough to overcome the repulsion, and no energy is gained. Fusion is not just a dream on Earth, it's what powers the stars, including our very own Sun. Every single second, the Sun fuses about 620 million metric tons of hydrogen and turns it into around 616 million metric tons of helium. The tiny difference in mass is released as energy, and that's what gives us sunlight and warmth. Even though the change in mass is small, only about 0.645%, it adds up to an enormous amount of energy. This energy travels through space as light and heat. One well-known example of fusion is when two hydrogen atoms fuse into helium. In that process, a small fraction of their mass is turned into energy. Some of it becomes light, and some becomes particles with a lot of movement, called kinetic energy. It takes a lot of energy to push two nuclei close enough to fuse, but once they get there, the strong nuclear force takes over, pulls them together, and releases energy. This kind of reaction is called exothermic, meaning it gives off energy. Fusion reactions are far more powerful than regular chemical reactions, like burning fuel. For example, when a hydrogen atom gains an electron, it releases only about 13.6 electron volts of energy. But a single deuterium-tritium fusion reaction releases 17.6 million electron volts, a difference of many millions of times. Fusion also packs more energy per kilogram than even nuclear fission, which is the process used in current nuclear power plants. While fusion turns about 0.7% of the mass of its fuel into energy, even that is tiny compared to the ultimate energy converters in the universe. Black holes and antimatter, which can convert up to 40% and 100% of mass into energy, respectively. If we could completely turn just 1 gram of matter into energy, it would release about 90 trillion joules, enough to power a whole city. Fusion is not just about energy. It's also how many of the elements in the universe were made. During the Big Bang and later inside stars, fusion built most of the elements lighter than iron. Heavier elements like gold and uranium were created through other cosmic events, like neutron-star collisions and supernovas, using processes called the S process and R process. As stars age and run out of hydrogen, fusion continues with heavier elements until no more energy can be produced. The life and death of stars, powered by fusion, are what created much of the matter that makes up planets, people, and everything we see around us. Way back in 1920, a scientist named Arthur Eddington had a brilliant idea. He believed that the power of stars came from turning hydrogen into helium, and that this released an enormous amount of energy. He didn't know all the details yet. At the time, even the idea that stars were mostly made of hydrogen wasn't fully accepted. But he was right. In a famous paper titled "The Internal Constitution of the Stars," Eddington guessed that this process worked according to Einstein's famous formula, which says that mass can be turned into energy. Eddington's prediction was one of the earliest and most accurate guesses about the true source of stellar power, even before fusion was fully understood. For a long time, scientists believed that stars got their energy from something called the contraction hypothesis. This idea said that as a star shrinks or contracts, it spins faster, just like a figure skater spinning faster by pulling in their arms. This is due to a rule in physics called conservation of angular momentum. But when astronomers observed a special type of star called Cepheid variable stars, they noticed something strange. The stars were not spinning faster at all. This meant the contraction hypothesis couldn't fully explain where stars get their energy. The only other reasonable explanation at the time was turning matter into energy. Several years earlier, Albert Einstein had shown through his famous equation that even a small amount of matter could be converted into a huge amount of energy. This was a big clue. Then came an important discovery by Francis Aston. He found that when 4 hydrogen atoms come together to form one helium atom, the total weight of the helium atom is actually about 0.8% less than the combined weight of the 4 hydrogen atoms. At the time, scientists thought that atomic weight was what made one element different from another. But later research by Henry Moseley and Antonius van den Broek showed that it's actually the number of positive charges in the nucleus, called the atomic number, that matters most. This meant that a helium nucleus had 2 hydrogen nuclei, protons, plus a bit of extra mass. Aston's discovery hinted at something powerful. If stars could somehow fuse hydrogen atoms into helium, they would release a lot of energy in the process. And that could be the true source of a star's power. Scientists worked out that if just 5% of a star's mass was made of hydrogen that could be fused, that would be enough to explain the star's brightness. Today, we know that most normal stars are made of about 70 to 75% hydrogen, which more than fits the bill. Some scientists even guessed that stars might be like cosmic ovens, where lighter elements like hydrogen and helium could combine to form heavier ones. But at the time, they didn't have precise enough tools to measure atomic masses, so they couldn't prove it yet. In the decades that followed, All of these guesses turned out to be correct. Now we know that stars, including our Sun, mainly get their energy through a process called nuclear fusion. Inside the Sun's core, where the temperature reaches about 14 million Kelvin, hydrogen atoms are squeezed together so tightly that they fuse into helium. This specific type of reaction is known as the proton-proton chain. When four hydrogen nuclei, protons, are fused together, they form one helium nucleus, also called an alpha particle. In the process, two positrons, the antimatter versions of electrons, and two neutrinos are released. These particles help change two of the protons into neutrons, and a lot of energy is released. In bigger and hotter stars, another process called the CNO cycle becomes more important. As stars start running low on hydrogen, they begin fusing heavier elements. In very massive stars, this eventually leads to silicon burning, which creates a buildup of iron and nickel. But there's a limit. Fusing anything heavier than nickel takes more energy than it gives, so stars can't do it efficiently. Heavier elements like gold, uranium, and lead are not made through normal fusion. Instead, they form during extreme cosmic events, such as supernova explosions, neutron star mergers, or in special slow and fast processes known as the S process and R process. Other types of stars behave differently. Brown dwarfs, which are like failed stars, can fuse a form of hydrogen called deuterium, and in the biggest brown dwarfs, even lithium. There are also white dwarfs, which are very dense stars about the size of Earth. If they pull in enough material from a neighboring star, they can reach something called the Chandrasekhar limit, which is about 1.44 times the mass of the Sun. Just before reaching this limit, a runaway fusion reaction can occur, destroying the white dwarf in a powerful explosion known as a type Ia supernova. Sometimes, two helium white dwarfs might merge. Instead of exploding, they can begin burning helium in a very rare type of star. Some neutron stars, even denser than white dwarfs, can steal hydrogen and helium from a nearby companion star. When enough helium builds up, a sudden burst of fusion can spread across the star's surface in just 1 second, releasing an enormous amount of energy. Fusion can even happen near black holes, especially in the superhot disks of gas swirling around them. Interestingly, these fusion reactions seem to be most powerful around black holes that are less than 10 times the mass of the Sun. Farther out from the center, beyond about 5 Schwarzschild radii, reactions like carbon burning and helium-3 fusion dominate. Closer in, elements like nitrogen, oxygen, neon, and magnesium can fuse, and in the most extreme cases, even silicon and selenium can be fused. Going way back to the early universe, between about 10 seconds and 20 minutes after the Big Bang, the entire cosmos cooled down from over 100 kilo-electron volts to just 1 kilo-electron volt. This drop in temperature allowed protons and neutrons to join together into deuterium, which then quickly fused into other light elements like tritium, helium-3, and mostly helium-4, with tiny traces of lithium, beryllium, and boron. But fusion isn't easy. Nuclei have positive charges, so they naturally repel each other. Getting them close enough to fuse requires overcoming this repulsion, which needs extreme heat and pressure. Fortunately, quantum physics gives fusion a little help. Particles can sometimes tunnel through this barrier, even if they don't have enough energy to climb over it. Inside a nucleus, nucleons, that is, protons and neutrons, stick together because of the nuclear force, which is a powerful but very short-range force. A nucleon mostly attracts the ones that are right next to it. This means that the nucleons in the middle of a nucleus are more tightly held than those on the surface. So, smaller atoms with more surface area compared to volume tend to have less binding energy per nucleon. As atoms get bigger, this binding energy increases, but eventually levels off when the nucleus is about the size of 4 nucleons in diameter. And here's something wild. Since nucleons like neutrons are quantum objects, they are completely identical. You can't tell one from another, and asking which one is on the surface and which is in the center doesn't even make sense. That's why we need quantum mechanics to properly understand and calculate how atomic nuclei behave. The electrostatic force is a kind of force that gets weaker as the distance between two charged particles increases. It's called an inverse square force because it follows the inverse square law. When the distance doubles, the force becomes 4 times weaker. In an atomic nucleus, protons are all positively charged, so they naturally repel each other due to this electrostatic force. When you add another proton to a nucleus, it feels a push away from all the other protons already there. This repelling force grows stronger as more protons are added, and the energy created by this repulsion, called electrostatic energy, increases more and more without any limit as the number of protons, also called the atomic number, gets bigger. Now, inside a nucleus, 2 main forces are at work: the repelling electrostatic force between protons and the strong nuclear force, which pulls protons and neutrons together. These 2 forces compete with each other. Because of this tug of war, the energy that holds the nucleus together, called binding energy, usually increases as the nucleus grows larger, but only up to a point. That point is around the elements iron and nickel. After that, for even heavier elements, the binding energy starts to go down. If a nucleus becomes too heavy, with more than 208 protons and neutrons combined, the forces can't keep it stable, and the nucleus may fall apart. That's why super-heavy elements are not stable in nature. Interestingly, among all the known nuclei, the 4 that are held together the tightest, meaning they have the highest binding energy per particle, are, in order, nickel-62, iron-58, iron-56, and nickel-60. Even though nickel-62 is technically the most stable of them, iron-56 is found in much greater amounts in the universe. That's because stars can't easily make nickel-62 through the normal process they use to build heavier elements, a process called the alpha process. There's also a curious exception to the general rule: helium-4. This tiny nucleus is more tightly bound than the next heavier element, lithium. Why? It comes down to how protons and neutrons behave. These particles are called fermions, and according to a rule in quantum physics called the Pauli exclusion principle, no 2 identical fermions can be in the exact same state in the same place. However, each energy level in the nucleus can hold 1 particle spinning up and 1 spinning down. The helium-4 nucleus has exactly 2 protons and 2 neutrons, and they fit perfectly into the lowest energy level. That makes it extremely stable. Scientists even treat helium-4 like a single particle in nuclear physics. It's known as an alpha particle. Now, imagine trying to bring 2 nuclei close together. As they approach each other, all the protons in one nucleus start pushing away all the protons in the other because of the electrostatic force. This creates what scientists call the Coulomb barrier. But if the nuclei get close enough, even just for a tiny moment, the strong nuclear force can suddenly take over and pull them together. Thanks to something called quantum tunneling, the particles can sometimes pass through this energy barrier even if they don't have quite enough energy to climb over it directly. The Coulomb barrier is smallest for hydrogen, which has the simplest nucleus, just 1 proton. A nucleus made of 2 protons alone, called a diproton, isn't stable. So to make fusion happen, neutrons also have to be involved, ideally in a way that creates helium, since helium has such a tightly bound nucleus. When scientists use a special kind of hydrogen fuel made of deuterium and tritium, 2 heavier forms of hydrogen, the energy needed to get fusion started is about 1/10 of 1 million electron volts. That's 0.1 MeV. To compare, it only takes 13.6 electron volts to knock an electron off a hydrogen atom. When deuterium and tritium fuse, they first create an unstable form of helium with 5 particles. This unstable nucleus quickly spits out a neutron carrying about 14.1 MeV of energy. The remaining helium-4 nucleus recoils with 3.5 MeV of energy. Altogether, this adds up to 17.6 MeV released, far more than the energy it took to get the reaction going. Now, scientists have a way to measure how likely fusion is to happen. This is called the reaction cross-section, often written with the Greek letter sigma. It depends on how fast the nuclei are moving toward each other. If the particles are part of a hot plasma, a gas so hot the atoms break apart, their speeds will vary. So scientists average out the product of sigma and the velocity and call this average reactivity. To figure out how many fusion reactions will happen in a given space and time, scientists multiply this reactivity by how many reacting nuclei are present. If the nuclei are of the same type, for example, two deuterium nuclei fusing together, then average relativity is nearly zero at room temperature, but it gets significantly higher when the temperature rises to between 10,000 and 100,000 electron volts. At such high temperatures, far beyond the energy that normally holds atoms together, the fuel exists as plasma. The way average relativity behaves at different temperatures, combined with how long the energy stays trapped in the system, leads to something called the Lawson criterion. This is a formula that tells us whether fusion can produce more energy than it uses. Meeting this requirement on Earth is incredibly hard, and that's one reason why scientists have spent many decades trying to make fusion energy a practical reality. Thermonuclear fusion is a powerful process where the nuclei of atoms are forced to combine, or fuse, together. But this doesn't happen easily. It takes extremely high temperatures to push these nuclei close enough for fusion to occur. When matter is heated to such extreme temperatures, it changes into a special state called plasma, where the particles move around with tremendous speed and energy. If this plasma is kept contained in one place, the particles might crash into each other with enough force to start fusion reactions. There are two main types of thermonuclear fusion. One is uncontrolled fusion, which happens naturally in most stars, including our Sun, and is also used in powerful weapons called hydrogen bombs. In these cases, the energy is released all at once and can't be controlled. The other type is controlled fusion, where scientists try to create and manage the fusion process in a way that lets them collect the energy and use it for useful purposes, like making electricity. Temperature is basically a way to measure how fast and energetic the particles in a material are moving. When you heat something up, its particles gain energy and move faster. In fusion, the material must be heated so much that the particles crash into each other hard enough to overcome the natural repelling force between atomic nuclei, known as the Coulomb barrier. The specific temperature needed for this to happen is determined by something called the Lawson criterion. For example, in a common fusion reaction that uses two types of hydrogen, deuterium and tritium, the particles must reach an energy of about 0.1 million electron volts. When converted into temperature, this means the plasma has to be hotter than 1,200,000,000 Kelvin. That's way hotter than the center of the Sun. Interestingly, fusion can still happen even if the plasma doesn't reach that extreme temperature. There are two main reasons for this. Not all particles are equal. Even if the average temperature is at a certain level, some particles will naturally have more energy than others. These extra energetic particles, those in what scientists call the high-energy tail, are the ones that are most likely to fuse. Quantum tunneling. This strange effect from quantum physics allows particles to sneak through the barrier even if they don't have quite enough energy. So, fusion can still occur at lower temperatures, just not as often. Thermonuclear fusion is one of the most promising methods scientists are exploring to generate clean, sustainable energy. If we figure out how to make it work reliably, it could greatly reduce carbon emissions and help fight climate change. One method for trying to create fusion is called accelerator-based light-ion fusion. In this approach, scientists use particle accelerators to speed up light ions, which are atoms with an electric charge, to very high speeds so that they can crash into each other and fuse. This process doesn't require complex machines, just a vacuum tube, two electrodes, and a high-voltage transformer. Fusion reactions can begin with as little as 10,000 volts between the electrodes. There are two ways this can be done. Beam target fusion, where fast-moving ions are aimed at a fixed target that contains fusion fuel. Beam fusion, where two streams of ions are shot toward each other so they collide in mid-air. However, this method has a major challenge. Most of the ions don't end up fusing. Instead, they lose their energy by giving off X-rays, Bremsstrahlung radiation, or by knocking electrons off atoms in the target. A special kind of machine called a sealed tube neutron generator uses this concept. It's a small particle accelerator filled with deuterium and tritium gases. Inside, ions are fired at targets that also contain fusion fuel, creating a burst of neutrons. These devices are made in large numbers each year, hundreds of them, for use in the oil industry, where they help locate and map oil reserves deep underground. Scientists have also tried to reuse the ions that don't hit their target. In the 1970s, a project called MIGMA tried to trap these ions in circular orbits using a magnetic ring, hoping they would circle back and eventually fuse. But studies showed that this idea wouldn't work well at the scale needed for energy production. Later, in the 1990s, physicist Norman Rostocker proposed using a new method called a field reversed configuration, FRC, which is still being studied by a company called TAE Technologies. A similar idea involves smashing together two spinning FRCs. This approach is being explored by another company called Helion Energy. Since these methods give ions much more energy than usual, they could make it possible to use alternative fuels, like proton-boron 11, which are too hard to use with other fusion systems. Fusion isn't just about making energy, it's also how scientists created new elements. Back in the early 1930s, researchers used deuteron beams to make elements like technetium, neptunium, and plutonium. Today, very heavy ions are used to discover super-heavy elements that don't exist naturally on Earth. There's another fusion method that works at room temperature. It's called muon-catalyzed fusion, and it was studied in the early 1980s by physicist Stephen Jones. This process uses particles called muons to help fusion happen without needing high heat. But there's a catch. Making muons uses a lot of energy, and they only last for about 2.2 millionths of a second. Plus, muons often get stuck to the fusion products and can't keep helping other reactions, so this method hasn't been successful for making energy. Scientists have come up with some other creative fusion methods too. Antimatter-initiated fusion. This idea uses tiny amounts of antimatter to start small fusion explosions. It's mostly been studied for space propulsion and weapons, but it's still too expensive to use for power. Pyroelectric fusion. In 2005, researchers at UCLA made fusion happen using a special crystal that created a strong electric field when its temperature changed. They heated the crystal from -34 degrees Celsius to 7 degrees Celsius, creating a field strong enough to accelerate deuterium ions into a metal target. Fusion occurred, producing helium and high-energy neutrons. However, the device used more energy than it produced, so it's only useful as a neutron generator, not as a power source. A hybrid nuclear power system, which combines both nuclear fusion and fission processes, has been suggested as a way to generate energy. This idea was first proposed in the 1950s and was briefly supported by Hans Bethe in the 1970s. However, it remained largely unexplored until 2009, when renewed interest emerged due to the slow progress in developing pure fusion energy. In the mid-1970s, Project PACER at Los Alamos National Laboratory, LANL, investigated a fusion power system that involved detonating small hydrogen bombs, also known as fusion bombs, inside underground chambers. This system was unique in that it was the only fusion power approach that could actually be demonstrated with existing technology. However, it had a major drawback. It would require a constant supply of nuclear bombs, making the economics of such a system questionable. Another idea that gained attention in the early 2000s was bubble fusion, or sonofusion. This process aimed to achieve fusion through sonic cavitation, where bubbles created in a liquid collapse under intense pressure and heat, potentially causing fusion. However, attempts to replicate the results failed, and the lead researcher, Rusi Talayarkhan, was found guilty of research misconduct in 2008. In stars, gravity naturally keeps the plasma contained, while in fusion reactors, magnetic forces are used. In inertial confinement, the fusion reaction happens so quickly that the inertia of the plasma itself holds it together before it can expand. Gravity is a force that can hold plasma together and meet the Lawson criterion, which is the threshold for achieving sustained fusion. However, the amount of mass required for gravitational confinement is enormous, so it is only found in stars. The smallest stars capable of maintaining fusion are called red dwarfs, while larger stars, like brown dwarfs, can fuse deuterium and lithium if they are massive enough. As stars grow larger and burn through their hydrogen fuel, they begin to fuse helium into carbon in their cores. In the largest stars, those with at least 8 to 11 times the mass of the Sun, this process continues, eventually producing energy by fusing lighter elements into iron. Once iron is formed, however, fusion reactions become endothermic. They absorb energy. So heavier elements are not formed during normal star evolution. Instead, elements heavier than iron are created in the violent explosions of supernovae. Some smaller stars also create these elements in their outer layers by absorbing energy and neutrons from fusion reactions taking place inside the star. Theoretically, all elements heavier than iron can release energy if split, as in nuclear fission, where energy is released by splitting heavy atoms. This energy has been stored for billions of years, ever since the elements were created during stellar nucleosynthesis, the process by which stars produce the elements. When electrically charged particles, like fuel ions, are present, they will follow magnetic field lines. This principle allows fusion fuel to be trapped using strong magnetic fields. Various magnetic setups can be used for this purpose, such as toroidal shapes in tokamaks and stellarators, or mirror confinement systems. Another approach to confinement is inertial confinement, which involves rapidly applying energy to the surface of a fusion fuel pellet. This causes the pellet to implode, increasing pressure and temperature to the point where fusion reactions can occur. To achieve these extreme conditions, the cold fuel must be explosively compressed. This principle is used in hydrogen bombs, where X-rays from a fission bomb drive the compression. It is also being explored in controlled fusion experiments using lasers, ion beams, electron beams, or Z-pinch devices. Conventional explosives can also be used to compress fuel to fusion conditions. For example, the UTIAS explosive-driven implosion facility has been used to generate stable, focused hemispherical implosions that produce neutrons from deuterium-deuterium fusion reactions. Electrostatic confinement is another method for confining fusion fuel, where ions are held using electrostatic fields. The most well-known device using this method is the fusor. In a fusor, positively charged ions are attracted to a negative inner cage, and as they collide, they can fuse. However, the fusor has limitations, such as high energy losses due to ion collisions and low fusion rates. To address these problems, researchers have proposed alternative designs, including using non-neutral clouds to generate the electrostatic field. These designs, such as plasma oscillating devices, penning traps, and polywells, are still in the experimental stage, and many challenges remain before they can be fully developed. The most famous approach to inertial electrostatic confinement, IEC, is the fusor. Since 1999, a number of enthusiasts have managed to perform amateur fusion using homemade devices. Other types of IEC devices include the polywell, mix pops, and marble concepts. In the cores of stars, fusion reactions happen very slowly due to the extreme conditions of temperature and density. For instance, In the Sun's core, where the temperature is about 15 million Kelvin and the density is around 160 grams per cubic centimeter, the energy produced by fusion reactions is only about 276 microwatts per cubic centimeter. This is roughly a quarter of the amount of heat a human body generates while resting. Therefore, trying to recreate the conditions of a star's core in a laboratory for power production through fusion is not practical. Since nuclear reactions depend on both temperature and density, and most fusion methods operate at relatively low densities, they rely heavily on achieving much higher temperatures. The temperature required in Earth-based reactors is between 10 to 100 times greater than the temperature found in the interior of stars, reaching around 100 million to 1 billion Kelvin. In artificial fusion, the fuel used isn't limited to protons, and higher temperatures can be reached. This allows for reactions that have larger cross-sections. A challenge in this process is the production of neutrons, which can activate the reactor structure, making it radioactive. However, neutrons are also useful because they allow for extracting energy from the fusion process and can help breed tritium, an isotope of hydrogen. Reactions that do not produce neutrons are known as aneutronic reactions. For fusion to be a useful source of energy, the reaction must meet several criteria. Exothermic. The reaction must release more energy than it consumes. This means that the reactants must be light elements on the low end of the periodic table, making helium-4 the most common product due to its tight binding. However, helium-3 and tritium also appear in some reactions. Involves low atomic number nuclei. The electrostatic repulsion between nuclei is determined by their number of protons, known as the atomic number. The lower the atomic number, the easier it is for the nuclei to come close enough to fuse. Has two reactants. At anything less than stellar densities, it is very rare for three nuclei to collide simultaneously. In inertial confinement, the density and temperature conditions are surpassed to make up for the lack of a third parameter in the Lawson criterion, which is the very short confinement time of fusion reactions. Has two or more products. This allows energy and momentum to be conserved without needing the electromagnetic force. Conserves protons and neutrons. The weak interaction in most reactions is too small to be considered significant. In reactions involving two products, the energy is shared between them in inverse proportion to their masses. For reactions involving three products, the energy distribution varies. In some reactions that can result in multiple sets of products, the branching ratios are used to determine the likelihood of each outcome. Certain reactions can be eliminated from consideration right away. For example, the deuterium-lithium-6 reaction has no advantage over the proton-boron-11 reaction because it is just as difficult to ignite but produces far more neutrons through side reactions involving deuterium. There is also a proton-lithium-7 reaction, but its cross-section is too low, except possibly when temperatures exceed 1 million electron volts. At such high temperatures, endothermic reactions that produce neutrons become a significant factor. Finally, there is the proton-beryllium-9 reaction, which is not only difficult to ignite, but also produces beryllium-9, which can easily split into two alpha particles and a neutron. In addition to fusion reactions, certain reactions with neutrons are important for producing tritium in dry fusion bombs and in proposed fusion reactors. For example, during the United States Castle Bravo fusion bomb test in 1954, which was the second ever fusion bomb test and the first to use lithium, the designers understood the role of lithium-6 in tritium production, but failed to realize that lithium-7 would significantly increase the bomb's yield. While lithium-7 has a small neutron cross-section at low neutron energies, it has a higher cross-section at energies above 5 million electron volts. This oversight led to a yield of 15 megatons, 150% higher than the predicted 6 megatons, resulting in unexpected fallout exposure. To evaluate the effectiveness of these reactions, several factors must be considered, including the reactants, the products, the energy released, and the nuclear cross-section. Each fusion device has a maximum plasma pressure it can sustain, and an efficient device will operate close to this maximum. At this pressure, the largest fusion output occurs when the temperature is chosen so that the ratio of the fusion cross-section multiplied by the velocity divided by the square of the temperature is maximized. This temperature also minimizes the value of the triple product required for ignition, as this value is inversely proportional to the cross-section to temperature ratio. A plasma is considered ignited if the fusion reactions generate enough power to maintain the temperature without needing external heating. Any of the reactions discussed could theoretically serve as the basis for fusion power production. Along with temperature and cross-section, we must also consider the total energy of the fusion products, the energy of the charged fusion products, and the atomic number of the non-hydrogenic reactant. The deuterium-deuterium reaction involves some challenges. First, it requires averaging over two possible branches of the reaction. A more difficult issue is the treatment of the tritium and helium-3 products. Tritium burns so efficiently in a deuterium plasma that it is nearly impossible to extract from the plasma. The deuterium-helium-3 reaction occurs at much higher temperatures, so its burn-up at the optimal deuterium-deuterium temperature may be low. Therefore, it is assumed that the tritium is consumed, adding its energy to the overall reaction, which results in a combination of the two branches of the deuterium-deuterium reaction. When calculating the reaction rate, it is important to consider that the deuterium-deuterium reaction involves only one reactant. This must be accounted for when determining the reaction rate. Finally, 4 of the most important reactions are summarized, with the last column showing the neutronicity, or the fraction of the fusion energy released as neutrons. This is a key factor in determining the challenges posed by neutrons, such as radiation damage, biological shielding, remote handling, and safety. For the first 2 reactions, neutronicity is calculated as the difference between the total fusion energy and the energy carried by charged products, divided by the total energy. For the last 2 reactions, where the calculation would yield 0, the values are rough estimates based on side reactions that produce neutrons in a plasma at thermal equilibrium. When trying to achieve fusion, it's important to mix the reactants in the right proportions. The ideal balance happens when each reactant ion, along with its electrons, contributes half of the total pressure. If we assume that the total pressure remains constant, it follows that the density of the non-hydrogenic ion, which is an ion that isn't made up of hydrogen, will be half that of the hydrogenic ion, which is made up of hydrogen. This ratio is represented by the factor 2 divided by the atomic number plus 1. As a result, the reaction rate for these non-hydrogenic ions is slowed down by this factor, in addition to any differences in how particles react at different temperatures. However, there is a positive side to this as well. A specific reaction, denoted as DD, has only one reactant involved, making its reaction rate twice as fast compared to when the fuel is split between 2 different hydrogen-based species. This makes the DD reaction more efficient. In essence, non-hydrogenic fuels come with a penalty because they need more electrons, which contribute to pressure but don't actually help with the fusion process. This penalty factor is 2 divided by the atomic number plus 1. It's commonly assumed that the temperature of the electrons is nearly the same as the temperature of the ions. But some scientists suggest the possibility that the electrons could be much colder than the ions, a condition known as hot ion mode, in which case this penalty would not apply. On the other hand, there is a bonus for reactions involving only one species, like the DD reaction, because each ion can react with any other ion, making the process more efficient. This penalty bonus factor indicates how much slower reactions are when they involve non-hydrogenic reactants or when only one species of fuel is used. To calculate this factor, we divide a number by the product of the second and third columns of data. This gives us an idea of how much slower other reactions are compared to the DT reaction, another fusion reaction, which is used as a standard comparison. The next column shows what's called the Lawson criterion, which adjusts the results based on the energy output of the reaction. This criterion tells us how much harder it is to achieve ignition starting a self-sustained fusion reaction with these alternative reactions, compared to the DT reaction. After that, there is a column labeled power density, which reflects how much practical energy is released by these reactions in comparison to the DT reaction. The final column shows how much lower the fusion power density is for these other reactions, providing a sense of their economic potential. In many fusion systems, ions, which are charged particles, are usually not alone. They're mixed with electrons, which balance out the overall electrical charge and form a plasma. These electrons typically have a temperature that's close to or higher than the ions. Because of this, they collide with the ions and emit X-rays, a type of radiation that carries energy away from the system. This is called Bremsstrahlung. In stars like the Sun, the size is so vast that the X-rays generated in this way don't escape, but instead deposit their energy back into the plasma. This makes stars opaque to X-rays. But for Earth-based fusion reactors, the X-rays escape because the reactor isn't large enough to trap them. These X-rays are hard to reflect, but are absorbed quickly by materials like stainless steel, which is used to shield the reactor. This absorption causes the plasma to cool down as the energy is lost to the surrounding walls. An important factor to consider when designing fusion reactors is the balance between the fusion power generated and the amount of energy lost as X-ray radiation. This ratio is usually optimized at a higher temperature than the one that maximizes the power density, the energy produced per unit volume. The table in the text shows estimates of the ideal temperature and power ratios for various reactions. However, the actual fusion to Bremsstrahlung power ratios are likely to be lower than these estimates for several reasons. First, the calculation assumes that the energy produced by the fusion process is entirely transferred to the fuel ions, which then lose energy to the electrons through collisions. But since the fusion products move faster than the fuel ions, they give up a significant portion of their energy directly to the electrons. Second, the ions in the plasma are assumed to be purely fuel ions, but in reality, there will be some impurity ions, which lower the ratio. Finally, other sources of energy loss besides Bremsstrahlung have been ignored. These last two factors are closely related because, in a good confinement system that keeps energy trapped, fusion products will accumulate. If these products are ejected efficiently, energy confinement will be poor too. For every fusion reaction, the temperatures that maximize fusion power compared to Bremsstrahlung losses are higher than the temperatures that maximize power density and minimize the requirements for energy confinement. While this doesn't greatly affect the DT reaction because Bremsstrahlung losses are low, it makes it harder to achieve high power density and energy confinement for other fuels. For reactions like DD and DHE3, Bremsstrahlung losses will be a significant problem. For other fuels like He3, He-Tigri, Pli6, and Pb11, these losses could make a fusion reactor using these fuels with a balanced plasma impossible. Some proposed solutions to this issue have been considered but ultimately rejected. This limitation does not apply to plasmas that are neither neutral nor isotropic, evenly distributed. But these types of plasmas come with their own set of challenges. In the classical view of fusion, atomic nuclei are seen as hard spheres that repel each other because of the Coulomb force, a fundamental force between charged particles. These nuclei only fuse once they get close enough to touch. If we estimate the size of an atomic nucleus to be about 1 femtometer, a millionth of a billionth of a meter, we find that the energy needed for 2 hydrogen nuclei to fuse is extremely high. In fact, if we were to use a simple model, the chances of hydrogen nuclei in the Sun fusing would be 10 to the power of negative 290, which is essentially zero. But in reality, fusion does occur in the Sun, thanks to the principles of quantum mechanics. Quantum mechanics increases the likelihood of fusion happening, because it allows for effects like the smearing of the nuclear radius due to the de Broglie wavelength and the process of quantum tunneling, where particles can pass through barriers that would be impossible to overcome in classical physics. The fusion rate depends on something called the cross-section, which measures the probability that particles will fuse when they collide. In systems where the particles are in thermal equilibrium, such as in the Sun or in fusion reactors, their energy follows a Maxwell-Boltzmann distribution, meaning the particles have a variety of energies around the average temperature of the plasma. To calculate the likelihood of fusion, scientists average the fusion cross-section across this range of energies, and these values are typically tabulated by research labs. Zero-point energy, often shortened to ZPE, is a fascinating idea from quantum physics. It refers to the lowest amount of energy that something can have in the quantum world. Now, in regular classical physics, we might think that a system at its lowest energy level would be completely still. But in the strange world of quantum mechanics, that's not the case. Even when a system reaches its lowest possible energy, it still vibrates and fluctuates. This unusual behavior is explained by something called the Heisenberg uncertainty principle. Because of this principle, even if we cool atoms and molecules all the way down to absolute zero, the coldest possible temperature, they still don't stop moving. They keep jiggling around ever so slightly. And here's where it gets even stranger. It's not just atoms and molecules that do this. Empty space itself, what we call the vacuum, also has this jittery, restless energy. According to a theory called quantum field theory, the universe is not made up of solid particles sitting in space. Instead, it's made of fields that are constantly vibrating. There are matter fields, which give rise to particles like electrons, quarks, and leptons, all called fermions, and force fields, which are behind the forces of nature and are connected to particles like photons and gluons, known as bosons. Every one of these fields has zero-point energy. Because these fields are always fluctuating, some scientists say it's like bringing back the old idea of the ether, a kind of invisible substance that fills all space. However, to avoid contradicting Einstein's theory of special relativity, this modern ether can't be treated like a physical material that we can move through or interact with directly. Zero-point energy plays an important role in cosmology, which is the study of the entire universe. But here's the problem. Physicists still don't have a complete theory to fully explain how zero-point energy fits into our understanding of the universe. In fact, there's a huge disagreement between the amount of vacuum energy predicted by theory and the much smaller amount we actually observe in the universe. This mismatch is one of the biggest puzzles in modern physics and is called the cosmological constant problem. Einstein's theory of general relativity says that any kind of energy, even vacuum energy, should affect gravity. We do have some evidence that supports the idea that vacuum energy is real, such as the expanding universe, the mysterious dark energy, and a small but measurable force called the Casimir effect. Still, the strength of this energy is surprisingly tiny. One possible explanation for the smallness of this energy is the idea that the energies from matter fields, fermions, and force fields, bosons, might cancel each other out. For example, fermions could have negative zero-point energy, while bosons have positive zero-point energy. If these perfectly balanced, the total energy would be zero. This idea would work only if a concept called supersymmetry were exactly true. Supersymmetry suggests that every particle has a hidden partner, but the Large Hadron Collider in Europe, which has been running since the early 21st century, has not found any evidence for this. Even if supersymmetry exists, it's probably broken and only works at extremely high energies, not in the everyday low-energy universe we live in. The phrase zero-point energy comes from the German word Nullpunktsenergie, which means energy at 0 point. Sometimes people also use other terms like ground state energy or zero-point radiation. When talking about the vacuum as a whole, scientists refer to something called the zero-point field, ZPF. This could be the quantum electrodynamics vacuum, QED vacuum, which deals with light and electrons, or the quantum chromodynamics vacuum, QCD vacuum, which handles the interactions between particles like quarks and gluons. So, in a sense, what we call empty space is actually a busy ocean of invisible fields and energies. In classical physics, we think of particles as having kinetic energy from motion and potential energy from position. Temperature, for instance, is a measure of how fast particles are moving around. At absolute zero, you'd expect everything to stop moving entirely. But thanks to the rules of quantum physics, even at this coldest temperature, particles still have some leftover movement. This leftover motion is the zero-point energy, and it never fully disappears. Why does this happen? It's again because of the uncertainty principle, which says you can never know both the exact position and speed of a particle at the same time. Because of this rule, quantum systems behave like tiny vibrating springs or waves. They are always a little uncertain, always in motion. So even in their lowest energy state, called the ground state, they still wiggle around. That's why something like liquid helium refuses to freeze at normal pressure, no matter how cold it gets. Its zero-point energy keeps it in motion. Einstein's famous equation, E equals mc squared, shows that energy and mass are two sides of the same coin. That means even a little bit of energy in a small part of space could, in theory, create mass or particles. Quantum field theory, QFT, was developed to explain how matter and forces interact at the smallest scales. It describes every point in space as a little vibrating oscillator. All these vibrating fields, matter fields and force fields, have zero-point energy. In fact, new experiments suggest that particles themselves may just be energetic ripples in this invisible quantum vacuum. That means what we see as stuff may simply be the result of fluctuations in the zero-point field. This idea that empty space isn't really empty is hard to imagine, but it's very important to how we understand the universe. Some scientists argue that the whole universe is soaked in a kind of background radiation made of zero-point energy. Even though this energy is everywhere, it can be hard to detect directly. Most of the time, physicists treat this energy as a constant that doesn't really affect calculations. But this leads to some problems, especially in general relativity, where the energy of space does matter. It actually shapes how space and time bend. For many decades, scientists hoped that some unknown principle would cancel out the infinite zero-point energy in equations, making it harmless. If this energy didn't really exist or had no absolute value, it wouldn't cause gravity. It was believed that as the universe expanded after the Big Bang, the vacuum energy would spread out and become weaker, slowing down the expansion of the universe. But in the year 1998, astronomers made a surprising discovery. The universe isn't slowing down, it's speeding up. That means empty space does contain some kind of energy that pushes everything apart. This energy is what we now call dark energy, and zero-point energy may be the best explanation we have for it. Still, it's a complete mystery why the energy we observe is so tiny compared to the massive amount that theory predicts. And so, the cosmological constant problem remains one of the biggest mysteries in science today. Many physicists believe that the answer lies hidden in the vacuum. The so-called empty space may, in fact, hold the key to understanding the universe itself. Many strange physical effects that scientists once thought were just theories about zero-point energy have actually been proven in real experiments. These include things like spontaneous emission, when atoms randomly give off light, the Casimir force, a tiny force that appears between two very close metal plates, the Lamb shift, a small change in the energy levels of electrons, the magnetic moment of the electron, which describes how an electron behaves in a magnetic field, and something called Delbruck scattering, which involves the bending of light by atomic fields. Scientists call these strange behaviors radiative corrections because they involve small changes caused by invisible particles and energy. In more complicated areas of physics, like quantum chromodynamics, or QCD, which studies the strong force that holds atomic nuclei together, zero-point energy plays an even bigger role. It can cause very puzzling effects like creating several stable states in a system, breaking natural symmetries, introducing chaotic behavior, and even making new properties emerge from the system that weren't obvious before. Scientists today are still exploring some deep and mysterious questions. They are trying to understand how zero-point energy is connected to virtual particles, particles that pop in and out of existence, quantum entanglement, where particles remain connected no matter how far apart they are, the difference between inertial and gravitational mass, do they really behave the same? Whether the speed of light can vary, why the cosmological constant has the value it does. This constant affects how fast the universe is expanding and what exactly dark energy is. The idea of zero-point energy didn't come out of nowhere. It grew from ancient ideas about the vacuum or empty space. Long ago, the Greek philosopher Aristotle called the vacuum to kenon, which meant the empty. He didn't believe in the idea of empty space because he thought it went against nature. Aristotle believed that everything was made up of continuous substances like fire, air, earth, and water, not tiny particles. But other ancient thinkers, called the atomists, believed that everything was made of atoms and that true emptiness existed. To them, emptiness was the space between things, a way to separate existence from non-existence. For a long time, this debate stayed in the world of philosophy. Real scientific progress didn't begin until the Renaissance. In the mid-17th century, a German scientist named Otto von Guericke built the first vacuum pump. This machine could suck the air out of a container, and for the first time, people could test the idea of emptiness in a laboratory. Scientists thought that if you removed all gases from a space, you could create a perfect vacuum, a space that was truly empty. This was the first widely accepted idea of what a vacuum was. However, by the end of the 19th century, scientists noticed something strange. Even if you removed all the gases from space, it still wasn't completely empty. There was still thermal radiation, heat energy left behind. At that time, the most popular explanation was the idea of the ether, an invisible substance that was believed to fill all space and carry light and other forms of energy. The famous physicist James Clerk Maxwell had created a theory where light was made of electromagnetic waves, and many thought these waves needed the ether to move through space. People believed that this ether wasn't truly empty, but full of energy and structure. But not everyone agreed. Maxwell himself admitted that the idea of ether was mostly made up to explain things we didn't fully understand. Then, in the year 1887, the famous Michelson-Morley experiment showed strong evidence that the ether didn't exist at all. This shook the scientific world and led to a new path of thinking. Eventually, this line of thinking brought about Albert Einstein's theory of special relativity, which completely removed the need for a stationary ether. After that, scientists started wondering, could we create a truly empty space by not just removing gases, but also by cooling the space down to remove all energy? This became the second big idea about creating a vacuum. If we could cool a region of space to absolute zero, the coldest possible temperature where no movement or energy remains, then we might finally have a perfect vacuum. But in the 19th century, scientists didn't yet have the technology to reach absolute zero, so the question remained unsolved. The idea of zero-point energy took shape in the early 20th century. In the year 1911, the German physicist Max Planck introduced the concept while trying to fix a problem in his earlier quantum theory from 1900. He realized that even in a vacuum, and even at absolute zero, energy still existed in small amounts. This tiny leftover energy became known as zero-point energy. Then, in the year 1912, Planck published a scientific paper where he explained how radiation was emitted in small bursts, or quanta. In his new theory, energy was taken in smoothly, but released only in fixed amounts, depending on a number called the frequency. According to this idea, even when no energy was added, a system still held a tiny bit of energy, a sort of built-in, leftover energy from the universe itself. This discovery led to what is now widely known as the birth of zero-point energy. Soon, other scientists became curious. In the year 1913, Albert Einstein and his assistant Otto Stern tried to prove that zero-point energy was real by calculating the specific heat of hydrogen gas and comparing it with real-world measurements. At first, they thought they had succeeded, but later they changed their minds, realizing that Planck's theory might not apply to the example they used. Einstein even wrote to another physicist saying that zero-point energy was dead as a doornail. But the idea didn't die. Other scientists picked it up. Peter Debye, for example, explained how zero-point energy in the atoms of a solid crystal could affect X-ray diffraction patterns, even when the crystal was cooled close to absolute zero. Then, in the year 1916, Walther Nernst suggested that empty space itself was filled with invisible electromagnetic energy. Later, when Einstein developed his theory of general relativity, he realized that even the vacuum of space had an effect on the universe. It could add to the energy that causes the universe to expand. This idea revived the thought that the vacuum had its own natural energy. In the early 1920s, two researchers named Kurt Benowitz and Francis Simon worked in Nernst's laboratory in Berlin. They studied how substances melted at extremely low temperatures. By measuring the melting points of hydrogen, argon, and mercury, they found evidence that zero-point energy was real. They also predicted, correctly, that this energy was the reason helium is so hard to freeze, even at the coldest temperatures. Later in the year 1934, Francis Simon confirmed their predictions. In the year 1924, another scientist, Robert Mulliken, gave direct proof that molecules have zero-point energy. He compared two versions of the same molecule, one made with a lighter type of boron and the other with a heavier type. He found that the energy differences between them would disappear if zero-point energy didn't exist. But since there was a difference, it proved that zero-point energy was real. Then, in the very next year, 1925, physicist Werner Heisenberg introduced a new way of understanding physics called matrix mechanics. This became one of the foundations of modern quantum mechanics. In his paper, Heisenberg showed that zero-point energy naturally arises from the rules of quantum physics. Back in the year 1913, a Danish scientist named Niels Bohr came up with a new way to understand atoms. His idea, now known as the Bohr model, imagined electrons, tiny particles with a negative charge, moving in specific orbits around the nucleus of an atom, kind of like planets orbiting the sun. But even with Bohr's model, scientists still had a big puzzle to solve. Why don't electrons just fall into the nucleus? According to the older, classical ideas of physics, anything with an electric charge that moves in a circle should gradually lose energy. If electrons were constantly losing energy, they should spiral inward and crash into the nucleus. If that happened, atoms wouldn't be stable, and neither would anything made of matter. This strange problem was pointed out clearly in 1915 by a British physicist named James Hopwood Jeans. He explained that if classical laws worked all the way down to the tiniest scales, opposite charges like protons and electrons would be pulled together with infinite force when they got very close. That would mean everything in the universe could just shrink away into nothing. It wasn't until 1926 that this mystery finally began to make sense. An Austrian physicist named Erwin Schrödinger introduced a groundbreaking idea called the Schrödinger equation. This new equation came from the strange world of quantum mechanics, a branch of physics that looks at how things behave at incredibly small scales. Schrödinger showed that electrons don't just follow classical rules. Instead, they behave like waves and have a certain quantum energy just from existing in a confined space near the nucleus. Even when they are at their lowest possible energy, they still have some energy left. This is called zero-point energy. Thanks to this strange but crucial concept, electrons can hover around the nucleus without falling in. And that's what keeps atoms and the entire material world stable. Also in 1926, another physicist named Pascual Jordan took things a step further. He tried to apply quantum rules not just to particles, but to fields of energy like the electromagnetic field, the force behind light and electricity. Working with two famous physicists, Max Born and Werner Heisenberg, Jordan imagined the field inside a box behaving like a collection of vibrating systems known as quantum harmonic oscillators. In doing this, Jordan found something strange. Even at absolute zero temperature, these systems still had an infinite amount of energy, what we now call zero-point energy. At first, Jordan didn't believe this was physically real. He even wrote to Albert Einstein, saying this infinite energy was probably just a mathematical oddity, not something that actually existed. Later, in 1928, Jordan teamed up with Wolfgang Pauli and figured out how to remove the infinity from the calculations. This process, now known as renormalization, became an important tool in modern physics. Around the same time, in 1927, another brilliant scientist named Paul Dirac made a huge leap forward. He created a theory that described how light interacts with matter at the quantum level. His theory, called quantum electrodynamics, QED, was the first to explain how particles like photons, the particles of light, could be created and destroyed. Dirac's theory showed that spontaneous emission, where an excited atom suddenly releases light, actually depends on the ever-present zero-point energy of empty space. In other words, even a perfect vacuum isn't really empty. It's full of tiny fluctuations of energy that can trigger events like the creation of light. In the 1940s, as technology improved, especially in the field of microwaves, scientists were able to make extremely precise measurements of atomic behavior. One of these was the Lamb shift, a tiny shift in the energy levels of a hydrogen atom. They also measured the magnetic moment of the electron, another small but important detail. These measurements didn't match Dirac's original theory exactly. To fix this, physicists brought back the idea of renormalization, removing the infinite energy terms in a careful way. The idea had been introduced earlier by Hans Kramers and Victor Weisskopf, but it was Hans Bethe in 1947 who successfully used it to calculate a realistic value for the Lamb shift. Even so, not all scientists agreed that zero-point energy was a real physical thing. Some thought it was just a trick of the math. Wolfgang Pauli, in his 1945 Nobel lecture, firmly stated that he didn't believe zero-point energy had any real physical existence. But then, in 1948, a Dutch physicist named Hendrik Casimir made a fascinating discovery. He showed that two uncharged flat metal plates placed very close together in a vacuum would feel a small but real attractive force. This force, now known as the Casimir effect, comes from the fluctuations of the zero-point energy in the empty space between the plates. At the time, Casimir had been studying colloids, thick liquids like paint or mayonnaise that contain tiny particles. A colleague named Theo Overbeek pointed out that the existing theory of how these particles interacted based on van der Waals forces didn't match the experimental results. To investigate, Casimir worked with another physicist, Dirk Polder, and they discovered that the theory only worked if they considered the fact that light doesn't travel instantly. It moves at a finite speed. After a chat with Niels Bohr, Casimir realized that their findings could be explained by zero-point energy. He wondered, if tiny particles felt this force, would it also happen between two mirrors facing each other in empty space? That question led to his prediction of the Casimir effect, a real, measurable force that arises out of what we usually think of as nothing. Later, in 1956, a scientist named Evgeny Lifshitz expanded this theory to include other types of materials, showing that both van der Waals and Casimir forces are part of a broader family of forces called dispersion forces. These forces become especially important at very tiny distances, about 100 billionths of a meter. So, from the mystery of stable atoms to the invisible energy of empty space, the idea of zero-point energy has taken scientists on an incredible journey. Whether it's helping explain how atoms behave, how light is created, or how even nothing can create a force, zero-point energy remains one of the strangest and most fascinating concepts in modern physics. Back in the year 1951, two scientists named Herbert Callan and Theodore Welton proved something called the quantum fluctuation dissipation theorem, often shortened to FDT. This idea was originally introduced in a simpler classical form in the year 1928 by a scientist named Nyquist. He came up with it while trying to explain a strange kind of noise called Johnson noise that showed up in electric circuits. Now, here's what the fluctuation dissipation theorem tells us in simpler terms. Whenever a system loses energy in a way that can't be reversed, what scientists call dissipation, there must also be some kind of random movement or fluctuation happening at the same time. In other words, when a system gives off energy, like heat or light, there's always a kind of jittery motion going on in the background. You can't have one without the other. They come as a package deal. This discovery had a fascinating implication. It suggested that the vacuum, the supposedly empty space all around us, could actually behave like a kind of heat bath, full of tiny fluctuations. And if that's true, then maybe, just maybe, we could find a way to tap into those tiny movements and extract some useful energy from empty space itself. Experiments carried out under certain strange quantum conditions, those that don't follow the usual rules of classical physics, have confirmed that FDT is actually true. That means this is more than just a theory. It works in the real world under the right conditions. Jumping ahead to the year 1963, another important model called the Jaynes-Cummings model was developed. This model described what happens when a simple two-level atom interacts with a field of light inside a tiny mirrored space known as an optical cavity. This setup produced some pretty surprising results. For instance, it showed that an atom could be made to release energy, a process called spontaneous emission, just by being surrounded by a light field of a steady frequency, something known as the Rabi frequency. During the 1970s, scientists began testing these strange ideas through actual experiments. They found that by placing atoms near reflecting surfaces, they could control how often those atoms gave off energy. At first, many scientists didn't believe this could be true. They wondered, how could the environment around an atom affect whether or not it releases a photon, if the atom can only see the environment by releasing that photon in the first place? But these experiments laid the foundation for a new field of study called cavity quantum electrodynamics, or CQED for short. This field explores how mirrors and cavities, basically enclosed spaces, can change the way atoms behave when they emit or absorb energy. For example, scientists learned that spontaneous emission could actually be slowed down or even stopped, a process known as inhibition. Or it could be made stronger. This was predicted way back in 1946 by a scientist named Purcell and is now known as the Purcell effect. Modern experiments have proven this effect is real, and it all ties back to how the vacuum or empty space interacts with atoms. Now, let's talk about zero-point energy. This is energy that exists even when everything else seems perfectly still. It's deeply connected to the famous Heisenberg uncertainty principle. That principle basically says that there are certain pairs of things, like a particle's position and speed, that you can never know perfectly at the same time. So, even in its calmest, lowest energy state, a system can never be completely still, because that would violate this uncertainty rule. What that means is that every system, even in its ground state, which is the state of least energy, must have a little bit of leftover energy, the zero-point energy. That's why no atom, particle, or field can ever be totally at rest. To make sense of this, physicists often use the idea of a quantum harmonic oscillator, which is kind of like imagining a particle bouncing back and forth in a springy well. Even when it reaches the bottom, it still wiggles a little bit because of quantum rules. This wiggle is where the zero-point energy comes from. In scientific terms, physicists use angular frequency, written as omega, to describe these wobbles. They also use a special version of Planck's constant called h-bar, which is just Planck's constant divided by 2 times pi. Using this, they describe the zero-point energy with a simple equation. E equals h-bar times omega divided by 2. Sometimes, a system can have more than one ground state. When this happens, the states are said to be degenerate. That means there's more than one lowest energy configuration the system can settle into. Degeneracy often shows up in systems where there's a special kind of symmetry, and that symmetry is tied to a special operator that doesn't change the system's energy. According to the third law of thermodynamics, when a system is cooled all the way down to absolute zero temperature, it settles into its ground state. The amount of disorder, or entropy, at that point depends on how many ground states the system has. A perfect crystal, for instance, has only one ground state, and therefore zero entropy at absolute zero. But some systems can have negative temperatures and still reach highly excited states, which is a very weird and special case. Now let's move into the world of quantum field theory, or QFT. This is the branch of physics that treats all particles and forces as vibrating fields spread out across space and time. In QFT, even what we call empty space isn't really empty. It's actually filled with countless tiny oscillators, like those springy systems we mentioned earlier, each contributing its own zero-point energy. According to this theory, the universe is made up of 3 kinds of fields. Matter fields. These include particles like electrons and quarks, and their building blocks are called fermions. Force fields. These are carried by bosons, like photons, which carry light, and gluons, which hold atomic nuclei together. The Higgs field, which is responsible for giving particles their mass, and its quantum is the Higgs boson. All of these fields have zero-point energy. The lowest energy state of each field is called its zero-point field, or ZPF. So the vacuum isn't empty. It's a bubbling sea of all these invisible fields in their ground states. In QFT, the zero-point energy of this vacuum state is called vacuum energy. When physicists talk about the average energy of this vacuum, they refer to it as the vacuum expectation value, or VEV for short. There are even special kinds of vacuum related to different forces. The QED vacuum deals with electromagnetic forces like those between photons and electrons, while the QCD vacuum handles the strong force that binds quarks together. Newer experiments suggest something even more astonishing, that particles themselves may just be ripples or disturbances in this underlying quantum vacuum. That means all matter, all the stuff around us, might simply be energy waves rising and falling in this invisible sea of fields. Here's where things get even stranger. When you add up the energy of every single point in space, using the formula E equals h-bar times omega divided by 2, you get an infinite amount of energy in any small space. That doesn't make sense in everyday terms, so physicists have to use a technique called renormalization to make the numbers work. Scientists do not all agree on how much energy actually exists in empty space, also known as the vacuum. According to quantum mechanics, the branch of physics that deals with the tiniest particles, there should be a huge amount of energy hidden in the vacuum. The famous physicist Paul Dirac once described it as a vast sea of energy. On the other hand, scientists who study general relativity, the theory that explains how gravity works, believe the energy in the vacuum must be much smaller. Otherwise, the shape and bending of space caused by gravity would not match what we observe in the universe. One way to understand this disagreement is by looking at a principle in quantum physics called the Heisenberg uncertainty principle. This rule says that it's possible for energy to suddenly appear out of nowhere for a very short time, as long as it quickly disappears again. So, even if the average amount of energy is small, there can be short bursts of large energy that still follow the rules of physics. To make sense of this confusing situation, scientists sometimes describe vacuum energy as something not entirely real, like a kind of virtual energy that contains both positive and negative parts. In a type of quantum theory called quantum perturbation theory, there is a common idea that the strange fluctuations in the vacuum, also called zero-point energy, can affect the behavior and mass of particles. These effects show up in diagrams that physicists use to visualize how particles interact, called Feynman diagrams. These diagrams often include loops, which represent the influence of this zero-point energy. The oldest and most well-known force field that scientists have studied in quantum terms is the electromagnetic field, the one responsible for light and electricity. The equations created by James Clerk Maxwell in the 19th century were once used to explain how this field behaves. However, those equations have now been replaced by something more advanced called quantum electrodynamics, or QED for short. Through QED, scientists discovered that even when there are no particles present, just a quiet, empty field, there is still some energy left over. This leftover energy is what we call zero-point energy, and it appears not just in the electromagnetic field, but in all fields studied by quantum physics. One fascinating thing about quantum fields is that they do not allow for perfectly defined states. For example, we cannot say exactly how many particles, like photons, are present and also know the exact shape of the field they belong to. This is because of the strange rules of quantum physics, which blend the ideas of waves and particles into something new. Instead of having clear answers, we work with something called probability amplitudes that describe the likelihood of certain outcomes. The actual shape of the field still follows classical, non-quantum rules, but the quantum properties are stored in special numbers called amplitudes that follow quantum laws. Now, the zero-point energy appears because two mathematical tools used in quantum physics, A and A+, pronounced a dagger, do not follow normal multiplication rules. This kind of behavior is common in quantum physics, especially in systems that behave like tiny vibrating springs, also called harmonic oscillators. The result of this odd behavior is that even when a system is in its lowest possible energy state, called the ground state, there is still some energy left, and that's what we call the zero-point energy. Some scientists believe that the entire universe is soaked in this zero-point energy, like an invisible ocean that's always there. But here's the catch. Because this energy is constant everywhere, it usually doesn't affect our measurements. We are only able to detect changes or differences in energy, not the steady background level. That's why physicists often choose to ignore the zero-point energy by simply declaring that the ground state has zero energy. This process, called normal ordering or Wick ordering, involves rewriting the equations in a way that removes the zero-point energy. A special symbol with double dots is used to show when this has been done. However, this shortcut does not solve everything. Even if we remove the zero-point energy from the equations, it finds its way back in. That's because when solving equations for how quantum fields behave over time, using something called the Heisenberg equations, we must include the vacuum field as part of the solution. This vacuum field helps maintain the internal logic of quantum physics and is necessary to preserve the mathematical rules known as commutators. So, the zero-point energy is not just something we can brush aside, it's built into the foundations of quantum field theory. There are two big questions we still need to ask. First, is the zero-point energy truly infinite, or is it just very large? When scientists try to measure this energy in a closed space, like a box with perfectly reflecting walls, they run into problems. Very high-energy waves can't actually be trapped inside such a box unless the walls are truly perfect, which is impossible. That means some of these waves are not countable, and we have to cut off the calculation at a certain point. This idea, called a cutoff, is often used to avoid infinite results. Now, if we expand this idea to the entire universe, things become even trickier. General relativity, which tells us that energy shapes the fabric of space itself, has to be taken into account. Theoretical physicist John Wheeler proposed the idea of geons, waves of energy that bend space but also leak out of any system trying to contain them. So again, a cutoff becomes necessary. Without it, the energy would be so high that it would start to bend space more and more, changing the very shape of the universe. This brings us to the second question: does the zero-point energy actually matter in real-world physics? In many practical calculations, scientists ignore it because energy is usually measured in terms of changes, not absolute amounts. So adding or subtracting a constant energy, even an infinite one, doesn't usually change the result. But in reality, energy is not always so easy to redefine. According to general relativity, the amount of energy in space affects its curvature. More energy means more curvature. In this context, the absolute amount of energy does matter, and it can't just be dismissed. Moreover, zero-point energy has been linked to real physical effects, like the Casimir effect, a force between two metal plates in a vacuum, the Lamb shift, a small change in the energy levels of electrons, and the anomalous magnetic moment of the electron. These effects show that zero-point energy is not just some mathematical trick. It has real, measurable consequences. The QCD vacuum is a specific type of vacuum found in quantum chromodynamics, QCD, the theory that describes how quarks interact with each other. Unlike other vacuum states, the QCD vacuum is special because it is filled with certain condensates, or energy patterns, like the gluon condensate and the quark condensate. These condensates play a crucial role in what is known as the confined phase of quark matter, where quarks are tightly bound together inside particles. In simple terms, gluons are the particles that carry the strong force, which holds quarks together in particles like protons and neutrons. Gluons are different from photons, which carry the electromagnetic force. While photons don't have an electric charge, gluons carry a special charge known as color charge, which allows them to participate in and mediate the strong interaction. This makes QCD far more complex than quantum electrodynamics, QED, the theory of electromagnetism, because QCD involves more complicated, non-linear equations. The standard model of particle physics proposes the existence of a field called the Higgs field. This field is unique because it has a non-zero value even in its ground state, when there is no energy or movement. This special property comes from the field's Mexican hat-shaped potential, where the lowest energy point is not at the center but at the edge. When the energy of the system falls below a certain incredibly high level, the Higgs field causes what is called spontaneous symmetry breaking, which leads to the creation of mass for certain particles. This process, known as the Higgs mechanism, happens when a field has a vacuum expectation value, meaning the field has a non-zero value even when it appears to be at rest. The massive bosons interact with the scalar field components of the Higgs field, which then couple to other particles through something called Yukawa coupling. This gives particles mass. The Higgs field is a key part of the standard model, and its value has been measured to be approximately 246 giga-electron volts per speed of light squared. This value is the only free parameter in the standard model that is not dimensionless, without units. The Higgs mechanism is related to superconductivity, which occurs when materials conduct electricity with zero resistance at very low temperatures. In this case, space itself can be seen as a medium filled with a sea of particles that interact with the Higgs field. This interaction prevents certain forces from traveling freely through space, similar to how electricity is blocked from moving easily in a superconducting material. Zero-point energy, the energy that remains in a system even when all particles are at their lowest possible energy state, has real physical effects. It's important to understand that zero-point energy is not just a mathematical concept that can be ignored or redefined away. It has significant consequences in real physics, and not accounting for it could lead to problems in future theories. For example, in general relativity, the zero-point energy of the vacuum contributes to a cosmological constant, a term that was introduced by Albert Einstein to balance his equations and describe a static universe. However, when we calculate the expected value of this zero-point energy, it turns out to be much larger than what observations suggest by about 120 orders of magnitude. This mismatch is known as the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. One well-known demonstration of zero-point energy is the Casimir effect, which was proposed by the Dutch physicist Hendrik Casimir in 1948. He predicted that the vacuum energy between two closely spaced metal plates would cause them to attract each other. The reason for this attraction is that the vacuum energy contains waves of all possible lengths, but some wavelengths are blocked by the plates. As the plates move closer together, more wavelengths are excluded and the vacuum energy decreases, which results in a force that pushes the plates together. The first experiments in the 1950s suggested that the Casimir force was real, but there was still some uncertainty about whether it was the only factor at play, as the experimental error was quite large. It wasn't until 1997 that Lamoureux showed definitively that the Casimir force was a real physical effect. Since then, the results have been confirmed in many experiments. In 2009, Munday and colleagues published results showing that, as predicted in 1961, the Casimir force can actually be repulsive as well as attractive. This could open up new possibilities for quantum levitation, where objects could float in a fluid, and could also lead to the creation of new types of nanoscale devices with extremely low friction. An interesting theoretical consequence of the Casimir effect is the Scharnhorst effect, which suggests that light might travel slightly faster than the speed of light between two closely spaced conducting plates. This is a purely theoretical idea, but it demonstrates the strange ways in which vacuum energy can influence the properties of space. Quantum fluctuations in the electromagnetic field, which are related to the zero-point energy of the vacuum, also cause other interesting effects. One of these is the Lamb shift, which causes tiny shifts in the energy levels of hydrogen atoms. This shift was not predicted by the original equations of quantum mechanics and was discovered through experiments. The shift is very small, about 4.38 millionths of an electron volt, or 1/10 millionth of the energy difference between two energy levels in the hydrogen atom. Part of this shift comes from the vacuum fluctuations of the electron-positron field, which acts like a dielectric constant, changing the way the electron interacts with the electromagnetic field. This effect is even more significant in muonic atoms, where a muon replaces the electron. In the presence of strong electric fields, it is believed that virtual particles can be separated from the vacuum, forming actual matter. This idea shows that electromagnetic radiation, which is light and other forms of energy, can turn into matter and vice versa. This realization brings about new aspects in the study of how light and energy interact, especially in a field called quantum electrodynamics. One key result of this discovery is that even in what seems like empty space, the basic equations we use to describe how electromagnetic fields behave must be replaced by more complex formulas. In these conditions, it becomes impossible to separate the behavior of empty space from that of matter, because electromagnetic fields can generate matter when the field's fluctuations are strong enough. This creates complicated interactions where gravity influences light and light also affects gravity. These effects were first predicted by Werner Heisenberg and Hans Heinrich Euler in the year 1936, and independently by Victor Weisskopf the same year. Weisskopf stated that The physical properties of the vacuum come from the zero-point energy of matter, which is influenced by missing particles and external field strengths, adding an extra term to the usual electromagnetic energy. This means that strong magnetic fields can change the energy in empty space. The point where electromagnetic fields are expected to become strongly nonlinear is known as the Schwinger limit. When this happens, the vacuum starts to behave like a special type of material, where you can observe the polarization of light change even in empty space. According to Albert Einstein's theories of special and general relativity, light should pass freely through a vacuum without being changed, a principle known as Lorentz invariance. However, in theory, if light interacts strongly enough due to quantum fluctuations, this principle could be violated. Most theories of quantum gravity suggest that Lorentz invariance is not a perfect rule in nature. It is believed that the speed of light through the vacuum could vary depending on its direction, polarization, and the strength of the magnetic field around it. Some studies have claimed to show evidence of this violation by finding changes in the polarization of light from distant galaxies. The first solid evidence of this was published in the year 2017, when astronomers looked at light coming from the star RxJ 185 6.5 to 3754, which is the closest known neutron star to Earth. Roberto Mignani, an astronomer leading the team from the National Institute for Astrophysics in Milan, commented that when Einstein created the theory of general relativity 100 years ago, he could not have predicted it would be used in GPS systems. The consequences of this discovery may only become clear over time. The team discovered that the visible light from the star had undergone a polarization of about 16%. If this effect had been caused by the light passing through interstellar gas or plasma, the polarization should have been no more than 1%. To confirm this discovery, similar observations need to be made using different wavelengths and other neutron stars. It is predicted that the polarization at X-ray wavelengths could be as high as 100%. Although no current telescope can measure this, new X-ray telescopes, such as China's Hard X-ray Modulation Telescope and NASA's Imaging X-ray Polarimetry Explorer, may soon be able to confirm this result. In the late 1990s, it was found that distant supernovae appeared dimmer than expected, suggesting that the expansion of the universe is speeding up, not slowing down as once thought. This led to a revival of the idea that Einstein's cosmological constant, which had long been assumed to be zero, might actually be a small positive number. This would mean that empty space itself has a form of energy, often referred to as dark energy. There is no clear explanation for the source of dark energy, but one possible explanation is that it comes from the zero-point energy of the vacuum. However, this guess is known to be off by 120 orders of magnitude. To investigate this, the European Space Agency launched the Euclid telescope on the 1st of July, 2023, with the goal of mapping galaxies up to 10 billion light-years away. By studying how dark energy affects the shape and arrangement of these galaxies, the mission will help scientists understand whether dark energy has changed over time. If dark energy is found to change, it could point to a theory called quintessence, where the acceleration is due to a type of energy from a scalar field instead of the cosmological constant. There is currently no evidence supporting quintessence, but it hasn't been completely ruled out either. The theory predicts that the universe's expansion should slow down a little more than what the cosmological constant suggests. Some scientists think the best evidence for quintessence might come from violations of Einstein's equivalence principle, which states that physical laws are the same everywhere, or from variations in the fundamental constants of nature over time or space. Scalar fields are predicted by both the standard model of particle physics and string theory, but a similar issue arises as with the cosmological constant. Theories suggest that scalar fields should have large masses due to zero-point energy. Cosmic inflation, a phase of rapid expansion right after the Big Bang, is believed to explain the large-scale structure of the universe. It is thought that quantum fluctuations from the zero-point energy during this inflationary period grew into huge cosmic structures, eventually forming galaxies and other objects in the universe. Many physicists also believe that inflation explains why the universe looks the same in every direction, why the cosmic microwave background radiation is evenly spread out, why the universe is flat, and why no magnetic monopoles have been observed. The exact cause of inflation is still not fully understood, though it shares similarities with dark energy and its effects. However, inflation is much more energetic and short-lived. Much like dark energy, one possible explanation is that it results from vacuum energy, which comes from tiny, unpredictable changes in the fabric of space known as quantum fluctuations. There is also a possibility that inflation played a role in baryogenesis, which is the theoretical process that created an imbalance between particles called baryons and their counterparts, antibaryons, in the very early universe. But this idea is not proven and remains uncertain. Paul S. Wesson explored what would happen to our understanding of the universe if we assume that zero-point energy, the lowest possible energy in a quantum system, is real. He faced several challenges, particularly with general relativity, which suggests that zero-point energy does not have gravitational effects, meaning it cannot behave like electromagnetic radiation. The idea of zero-point energy has sparked a long debate. Scientists question whether zero-point fluctuations, small, random changes in energy within a vacuum, are truly real, or if they can be explained in other ways by alternative theories. A scientist named Julian Schwinger, for example, tried to explain quantum electrodynamics, QED, without relying on zero-point fluctuations, using what he called source theory. From this approach, he was able to explain the Casimir effect, a phenomenon where two closely spaced plates in a vacuum experience an attractive force without needing to refer to fluctuating fields. Schwinger first offered this explanation in 1975 for a simple, non-interacting field, and later extended it to electromagnetic fields in 1978. In their work, Schwinger and his colleagues claimed that the vacuum, in this view, is simply a state where all physical properties are equal to zero. In 2005, Robert Jaffe suggested a similar point, arguing that zero-point fluctuations are a useful tool for understanding the Casimir effect, but are not strictly necessary for the theory of quantum electrodynamics. On the other hand, Milani demonstrated that vacuum fields are essential for the mathematical consistency of quantum electrodynamics. Modern physics doesn't have a better way to create theories that can be adjusted and made to fit real-world observations than by using zero-point energy. It seems that zero-point energy is crucial for any attempt at a unified theory of physics. However, Jaffe emphasized that no experiment, including the Casimir effect, has proven that zero-point energy is real in a physical sense. Classical electromagnetism, quantum electrodynamics, and the Standard Model all treat the electromagnetic vacuum as a simple, linear system with no observable effects. For instance, phenomena like the Casimir effect or the Lamb shift, another effect that changes the energy levels of hydrogen atoms, could be explained by other mechanisms, which don't require the vacuum to have these random fluctuations. This is part of how electromagnetism is modeled as a U1 gauge theory, which doesn't allow the field to interact with itself in complex ways. However, in higher symmetry theories, the vacuum isn't just a calm, passive, random background. It can be seen as a turbulent, virtual plasma with complex structures like vortices and entangled states, similar to particles. These theories suggest that the electromagnetic field may have real, physical properties. Observations of various electromagnetic phenomena, such as the Aharonov-Bohm effect, the Josephson effect, and the quantum Hall effect, point to the idea that the electromagnetic field does not simply serve as a mathematical concept, but could be a real force. This means that a more complete theory of electromagnetism could treat it as a more complex system, perhaps using higher symmetries like SU2 gauge theory, allowing for non-linear behavior, multiple stable states, chaos, and other unexpected phenomena. The way nature is organized, from galaxies to human consciousness, can be understood as a series of systems that naturally dissipate energy, increasing entropy across the universe. For example, it has been estimated that the human body is about 10,000 times more effective at dissipating energy per unit of mass than the Sun, showing how complex systems help drive the flow of energy through the universe. One might wonder how this connects to zero-point energy. In recent years, researchers have been paying close attention to a new type of phase transition that happens at absolute zero temperature, the lowest possible temperature. These are called quantum phase transitions, and they occur because of electromagnetic field fluctuations, which are a result of zero-point energy. An example of a phase transition that occurs due to zero-point fluctuations is found in superconductors. Superconductivity is one of the most well-known electromagnetic phenomena, and it has been carefully studied. It's known that superconductivity has a quantum mechanical foundation. The behavior of electric and magnetic fields in superconductors is explained by the London equations. However, some scientists have questioned whether these equations, which are accepted in quantum mechanics, can be derived from classical physics alone. For example, Bostick has argued that the London equations actually have a classical origin and can apply to both superconductors and certain types of plasmas. He suggests that the Beltrami vortices in plasma focus systems have a structure that resembles the flux tube arrangement seen in Type II superconductors. Other scientists, like Fröhlich, have pointed out that the equations for compressible fluids, when combined with the London equations, can explain the macroscopic properties of superconductors without using quantum mechanical concepts like phase factors or the Planck constant. Essentially, some believe that the vortex structures found in plasma can imitate the shape of superconductors. This happens because the energy of the vortex, which involves ions and electrons, is much more organized than the random thermal energy, which is less structured. The transition from random fluctuations to organized helical structures is a phase transition, where the system's energy changes without any increase in temperature. This illustrates how zero-point energy can have multiple stable states. In this context, the structure of the system does not depend on a reductionist or deterministic view. The classical order of the system can even affect quantum phenomena. Interestingly, the creation of Beltrami vortices has been compared to how virtual particles are produced in a vacuum. The idea that vacuum energy can have multiple stable states is a leading explanation for cosmic inflation. Some scientists believe that these early fluctuations in vacuum energy caused the universe to expand, and this expansion set up the conditions necessary for complexity to emerge. Without this expansion, the universe would have reached a state of equilibrium where no complexity could form. As the universe continues to expand, it creates an energy gradient that allows more free energy, the usable energy available for work. This energy enables the universe to form even more complex structures. The only reason Earth's environment hasn't fallen into equilibrium is because it receives energy from the Sun. The Sun, in turn, contributes to interstellar entropy or disorder. The Sun's ability to produce energy through nuclear fusion is made possible by the gravitational imbalance of matter that was created during the cosmic expansion. In this way, vacuum energy can be seen as the key factor in the creation of structure throughout the universe. The idea that humanity could manipulate vacuum energy to create energy gradients for useful work remains a topic of debate. Despite skepticism from most physicists, some are still interested in harnessing zero-point energy, often considering it a fringe science. As far back as 1889, before quantum theory and the discovery of zero-point energy, Nikola Tesla suggested that useful energy could be extracted from empty space, or what was then believed to be an all-pervading ether. Since then, others have claimed to have discovered ways to exploit zero-point or vacuum energy, though much of the literature around this topic is considered pseudo-scientific and has been ridiculed. Despite this, the idea of using zero-point energy continues to attract researchers' interest, particularly in the United States, where it has captured the attention of aerospace and defense contractors, the US Department of Defense, and countries like China, Germany, Russia, and Brazil. Some argue that the Casimir force, a phenomenon related to zero-point energy, has no practical use because to get energy from it, the two plates involved would need to come together, and separating them would require even more energy. Thus, the Casimir force is often seen as a one-time phenomenon. However, in 1984, Robert Forward proposed a method for creating a vacuum fluctuation battery that could be recharged by strengthening the electrical forces to push the plates apart again. In 1999, a former scientist from NASA's Jet Propulsion Laboratory, Pinto, published a thought experiment in Physical Review, suggesting that a Casimir engine could work. He claimed that it was possible to continuously extract energy from the Casimir effect, stating in the abstract that if no other explanations could be found, this could lead to major advances in creating endless, byproduct-free energy. Garrett Model from the University of Colorado has pointed out that such devices would rely on the assumption that the Casimir force is non-conservative, meaning it doesn't lose energy over time. However, Model argues that the Casimir force is actually conservative, meaning that while it can be used for work, it cannot produce more energy than is put into the system. In 2008, DARPA, the Defense Advanced Research Projects Agency, invited researchers to submit proposals focused on a concept called Casimir Effect Enhancement, CEE. The main aim of this program was to discover new techniques for controlling and manipulating the forces of attraction and repulsion between surfaces, specifically by using the Casimir force, a fundamental quantum effect. In the same year, a patent was filed by scientists Heisch and Model, detailing a device that could potentially harvest power from zero-point fluctuations, a mysterious form of energy believed to exist even in empty space. This device used a gas circulating through a specially designed Casimir cavity. By 2012, Model tested this idea, and the results appeared to show an excess of energy that couldn't be explained by conventional sources. However, it was still uncertain whether this energy truly came from zero-point energy, and more research is needed to confirm the findings. Going back in time, in 1951, Callan and Welton proved a theory known as the fluctuation dissipation theorem, FDT. This theorem, first introduced in a classical form by Nyquist in 1928, provided an explanation for an effect called Johnson noise, which is observed in electrical circuits. The theorem explained that when a system loses energy in a way that can't easily be reversed, the surrounding environment, referred to as a heat bath, also experiences fluctuations. These fluctuations are tightly linked to energy loss, and they cannot occur separately. The implications of this are far-reaching, suggesting that it might be possible to extract energy from the vacuum of space, treating it as a heat bath connected to a dissipative force. However, not everyone agrees with this idea. In the early 1960s, scientists McDonald and Harris argued that extracting energy from zero-point fluctuations is impossible, and thus FDT could not be true. Later, in the 1980s, Grau and Klein, as well as Klein again in 1986, pointed out that the Johnson noise from a resistor connected to an antenna had to follow a thermal radiation formula developed by Planck. According to them, this meant that at absolute zero temperature, the noise should disappear, which would invalidate FDT. In 1988, Kiss suggested that the zero-point term might be a mathematical problem, not something real, similar to issues seen in quantum electrodynamics. Then, in 1996, Abbott and others offered a different, unclear interpretation, claiming that zero-point energy could be infinite and needed to be renormalized, but the fluctuations themselves should not be. Despite the criticisms, experimental evidence has supported the FDT under certain conditions that go beyond classical physics. The idea that zero-point fluctuations can contribute to systems that lose energy is increasingly accepted. For example, a study by Armin Alaverdian and Theo Nieuwenhuizen in 2000 showed how zero-point energy could potentially be harnessed for useful work from a single heat bath without violating the laws of thermodynamics by making use of certain quantum properties. Furthermore, over the years, a number of studies have emerged suggesting that in some specific situations, the classical laws of thermodynamics, such as the limits on efficiency set by the Carnot cycle, might be bypassed by taking advantage of negative entropy linked to quantum fluctuations. Despite these promising developments, the relationship between quantum mechanics and thermodynamics remains a big mystery. We still don't fully understand how quantum effects might change classical thermodynamic boundaries, and this is a question that continues to puzzle scientists. As for the idea of using zero-point energy for space travel, it's still mostly speculative and not widely accepted by mainstream science. There is no complete theory of quantum gravity yet, one that would explain how phenomena like zero-point energy fit into our understanding of gravity. Some speculative papers have suggested possible connections between zero-point energy and gravitational effects like shielding, but these ideas are far from proven. According to Einstein's general theory of relativity, rotating masses can create a new kind of force known as the gravitomagnetic interaction, which depends on the rate of spin. Under certain circumstances, this gravitomagnetic field can even be repulsive. In the case of neutron stars, this interaction might produce a kind of gravitational Meissner effect, though the force in this scenario is thought to be incredibly weak. In 1963, Robert Forward, a physicist and aerospace engineer, proposed that anti-gravitational effects could potentially be achieved within the framework of general relativity. He suggested that since all atoms have spin, different materials might have different gravitational properties. Materials that enhance time-varying gravitational fields could potentially create a strong toroidal gravitational field that would oppose gravity, similar to how iron works in an electromagnetic transformer. 3 years later, in 1966, DeWitt first recognized the role of gravitational effects in superconductors. He demonstrated that such materials would experience fluxoid quantization, a key concept in understanding quantum gravitational effects. Later, in 1993, Scharnhorst and Barton demonstrated that the speed of light could increase when photons travel between two Casimir plates, a sign of negative energy. This discovery was part of a broader theory involving exotic matter with negative energy, which could, in theory, enable the creation of wormholes, tunnels in space-time that could potentially allow for faster-than-light travel. This exotic matter would share properties with other mysterious forms of energy, like dark energy or zero-point radiation, that exist in the vacuum of space. In the year 1992, Evgeny Podkletnov published a highly controversial article that stirred much debate. He claimed that a special type of rotating superconductor might have the ability to block or shield gravitational force. Around the same time, from 1991 to 1993, two researchers, Ning Li and Douglas Torr, published several articles about how gravity might interact with superconductors. One important discovery they made was that the magnetic effects of gravity, known as gravitomagnetic flux, in a particular kind of superconductor material, come from the way the spins of the atoms are arranged. As they explained in their third paper, it is shown that the alignment of the spins of the atoms in a material will produce a detectable gravitational magnetic field, and when a changing magnetic field is applied, a detectable gravitational electric field will appear. While some people questioned the size of the force they claimed to observe, others supported the results. In 1997, Li published a paper where she tried to repeat Podkletnov's experiments. She found that the effect was either too small to measure or perhaps didn't exist at all. It is said that Li left the University of Alabama in 1999 to start her own company, AC Gravity LLC. In 2001, AC Gravity received a government grant from the US Department of Defense for about $448,000 to continue researching anti-gravity. However, when the grant period ended in 2002, no public results from their research were made available. In 2002, a division of Boeing called Phantom Works, which focuses on advanced research, approached Evgeny Podkletnov. However, due to restrictions on the transfer of Russian technology, the project faced hurdles. Lieutenant General George Molnar, the head of Boeing Phantom Works at the time, confirmed that Boeing's attempts to collaborate with Podkletnov had been blocked by the Russian government. He also commented that the physical principles, and Podkletnov's device is not the only one, appear to be valid. There is basic science there. They're not breaking the laws of physics. The issue is whether science can be engineered into something workable. In 2002, Froning and Roach published a paper building on the work of scientists like Puthoff, Heisch, and Alcubierre. They used computer simulations to study how a spacecraft, like the one proposed by Alcubierre, might interact with the zero-point field. They modeled the effects of the vacuum on the vehicle's motion and compared it to the force exerted by the zero-point field. Their findings showed that the kind of negative energy needed for Alcubierre's concept would work best with a saucer-shaped craft surrounded by special electromagnetic fields. These fields could distort the surrounding vacuum, altering the very nature of space itself. Then, in 2009, researchers Giorgio Fontana and Bernd Binder introduced a new idea to potentially tap into the zero-point energy of the electromagnetic field and nuclear forces in the form of gravitational waves. They referred to a model of the atomic nucleus proposed by the famous scientist Linus Pauling, which includes dineutrons, tiny particle pairs that could be sources of gravitational waves at extremely high frequencies, like X-rays and gamma rays. The motion of dineutrons within a nucleus could generate these waves, which could be produced by the way nuclear forces interact with them. Although gravitational waves are understood well in terms of general relativity, which is not a quantum theory, Fontana and Binder's approach suggests that nuclear species that are unstable and linked to zero-point energy may emit these waves. This idea has not yet been explored in experimental physics. Finally, in 2014, NASA's EagleWorks laboratories made an exciting announcement. They had successfully tested a quantum vacuum plasma thruster, which works using the Casimir effect for propulsion. In 2016, a peer-reviewed scientific paper from their team was published, marking a significant step forward. The paper suggested that the zero-point field could act like a pilot wave, and that the thrust from their device might be caused by particles pushing off the quantum vacuum. While peer review does not guarantee a finding is correct, it does show that other scientists have examined the work carefully and found it plausible. The researchers acknowledged 9 possible sources of error, including things like air currents and electromagnetic interference, and they noted that more testing would be needed to confirm the results and rule out these possible errors. Geothermal energy is heat that comes from deep within the Earth. This energy is a mix of heat from the planet's original formation and from the decay of radioactive materials. People have been using geothermal energy for thousands of years. For example, hot springs have been used for bathing since the Paleolithic era, and since Roman times, geothermal energy has been used to heat spaces. Geothermal power, which involves turning geothermal energy into electricity, has been used since the 20th century. Unlike wind or solar energy, geothermal plants can produce electricity all the time, regardless of weather. Geothermal resources are more than enough to meet humanity's energy needs, and most of the energy is extracted from places near tectonic plate boundaries. The cost of generating geothermal electricity dropped by 25% during the 1980s and 1990s. Thanks to advances in technology, costs kept going down, and more geothermal resources became available. By 2021, the US Department of Energy estimated that geothermal power from a plant built that year would cost about 5 cents per kilowatt hour. In 2019, there were 13,900 megawatts of geothermal power available worldwide. Another 28 gigawatts were being used for heating homes, spas, industrial processes, desalination, and farming by 2010. By 2019, around 100,000 people were working in the geothermal energy industry. Hot springs have been used for bathing for at least as long as the Paleolithic period. The oldest known spa is found at the Huaqing Palace in China. In the 1st century of the Common Era, the Romans took over Aquae Sulis, which is now the city of Bath in England. There, they used hot springs to heat public baths and floors. The fees charged for using these baths might be the first recorded commercial use of geothermal energy. The world's oldest geothermal district heating system has been running since the 1500s in Chaude-Aigle, France. The first industrial use of geothermal energy began in 1827 when geyser steam was used to extract boric acid from volcanic mud in Larderello, Italy. In 1892, Boise, Idaho, became the first city in the US to use geothermal energy for district heating. This system was copied in Klamath Falls, Oregon in 1900. The first known building to use geothermal energy for its primary heating source was the Hot Lake Hotel in Union County, Oregon, which started using geothermal energy in 1907. In 1926, a geothermal well was used to heat greenhouses in Boise. Around the same time, geysers were heating greenhouses in Iceland and Tuscany, Italy. In 1930, Charles Lieb developed the first downhole heat exchanger to heat his house. By 1943, geyser steam and water began heating homes in Iceland. In the 20th century, geothermal energy began being used to generate electricity. On July 4, 1904, Prince Piero Ginori Conti tested the first geothermal power generator at the Larderello steam field in Italy. The generator successfully lit 4 light bulbs. In 1911, the first commercial geothermal power plant was built at the same location. This was the only plant producing geothermal electricity until 1958, when New Zealand built a plant. By 2012, the Larderello plant was producing about 594 megawatts of electricity. In 1960, Pacific Gas and Electric opened the first U.S. geothermal power plant at the Geysers in California. The original turbine ran for over 30 years, producing 11 megawatts of net power. In 1967, the USSR demonstrated the first organic fluid-based binary cycle power station, and in 1981, this technology was introduced to the US. This system made it possible to generate electricity from geothermal resources as low as 81 degrees Celsius. In 2006, a binary cycle plant in Chena Hot Springs, Alaska, began producing electricity from a record low temperature of 57 degrees Celsius. The Earth holds an immense amount of heat, around 1,031 joules, or 3 times 10 to the power of 15 terawatt-hours. About 20% of this heat comes from the planet's formation, and the rest is from the decay of naturally occurring radioactive materials. For example, a deep borehole drilled to 5,275 meters in the United Downs. Deep Geothermal Power Project in Cornwall, England, discovered granite with a high amount of thorium, a radioactive element believed to contribute to the rock's high temperature. The temperature and pressure inside the Earth are so high that some rocks melt and the solid mantle behaves like a thick flowing liquid. Parts of the mantle rise because they are lighter than the surrounding rock. At the boundary between the Earth's core and mantle, temperatures can exceed 4,000 degrees Celsius, 7,230 degrees Fahrenheit. Heat from the Earth's interior moves to the surface at a rate of 44.2 terawatts and is replenished by the radioactive decay of minerals at a rate of 30 terawatts. This flow of energy is more than double the current total energy usage of humanity, though most of this energy cannot be captured. On top of the internal heat, the Earth's surface is also heated by the sun, especially in the summer. In the winter, the surface cools. The geothermal gradient, or the rate at which temperature increases with depth, is usually around 25 to 30 degrees Celsius per kilometer of depth. The heat flow from the Earth's interior averages about 0.1 megawatt per square kilometer. These values are much higher near tectonic plate boundaries, where the Earth's crust is thinner. Heat can also be increased by the movement of fluids, such as magma, hot springs, or hydrothermal circulation. To generate electricity efficiently, geothermal systems rely on high heat sources, such as hot springs. A common method is to drill wells into hot water aquifers. Another option is to inject water into rocks to create an artificial reservoir known as an enhanced geothermal system. In 2010, estimates of geothermal electricity generation potential ranged from 0.035 to 2 terawatts, depending on the level of investment. Deeper wells, up to 10 kilometers deep, could tap into even more geothermal energy. These deep wells are common in the petroleum industry. By 2010, geothermal electricity was being generated in 26 countries around the world. As of the year 2019, the total geothermal power capacity around the world reached 15.4 gigawatts. Out of this, the United States accounted for nearly 1/4, which is about 3.68 gigawatts. Geothermal energy provides a substantial amount of electricity in countries like Iceland, El Salvador, Kenya, the Philippines, and New Zealand. Geothermal power is considered a renewable energy because the rate at which heat is extracted from the Earth is incredibly small compared to the total amount of heat the Earth contains. On average, geothermal power plants release only about 45 grams of carbon dioxide for every kilowatt-hour of electricity they generate. This is less than 5% of the carbon dioxide emissions from coal-fired power plants. Historically, geothermal power plants were built along the edges of tectonic plates where the Earth's heat comes closer to the surface. However, thanks to advances in technology, including the development of binary cycle power plants and improved drilling methods, geothermal power plants can now be located in many more areas. Demonstration projects are currently operating in places like Landau-Pfalz, Germany, and Sault-sous-Forêt, France. Earlier, a project in Basel, Switzerland, was shut down after it caused earthquakes. Additional demonstration projects are under construction in countries such as Australia, the United Kingdom, and the United States. In Myanmar, over 39 locations have the potential to produce geothermal energy, including some near the city of Yangon. Geothermal heating involves using the Earth's heat to warm buildings and water for everyday human use, a practice that dates back to the Paleolithic era. In the year 2004, about 70 countries used geothermal energy directly, totaling approximately 270 petajoules of geothermal heating. By the year 2007, geothermal heating provided around 28 gigawatts of energy, fulfilling about 0.07% of the world's total energy needs. Geothermal heating is highly efficient because no energy conversion is needed, though it typically operates at lower capacity during the warmer months since the heat is most needed in the winter. Even ground that feels cold has heat beneath the surface. For example, if you go down just 6 meters, or 20 feet, the temperature of the Earth remains stable and can be used with a ground source heat pump to extract heat. Hydrothermal systems generate geothermal energy by tapping into natural underground reservoirs of hot water or steam. These systems come in 2 types: vapor-dominated and liquid-dominated. The well-known geothermal sites at Lardorello and the geysers are vapor-dominated, meaning they produce superheated steam at temperatures ranging from 240 to 300 degrees Celsius. Liquid-dominated reservoirs, which are more common, can produce temperatures higher than 200 degrees Celsius and are typically found near volcanoes in areas like the Pacific Ocean or in geological rift zones. Flash plants are commonly used to convert this steam into electricity. Most geothermal wells produce between 2 and 10 megawatts of electricity, with the steam driving generators. After the steam is used, the remaining water is sent back down the well to be reheated. By 2013, the largest liquid-dominated system in the world was located in Cerro Prieto, Mexico, where temperatures can reach 350 degrees Celsius and it generates 750 megawatts of electricity. For lower temperature liquid-dominated reservoirs, typically between 120 and 200 degrees Celsius, water must be pumped to the surface. These systems are commonly found in regions where the heat is accessed through deep circulation along fault lines, like in the western United States and Turkey. A Rankine cycle binary plant is used, where water circulates through a heat exchanger and vaporizes an organic fluid, which then powers a turbine. These plants, which first appeared in the Soviet Union in the late 1960s, have no harmful emissions. An engineered geothermal system refers to a geothermal system that has been enhanced or artificially created by engineers. These systems are used in areas where natural geothermal reservoirs may not be sufficient for energy production, such as when the hot rocks are not permeable or the amount of geofluid is too low. Types of engineered geothermal systems include enhanced geothermal systems, EGS, closed-loop systems, and superhot rock systems. In enhanced geothermal systems, engineers inject water into deep wells under high pressure, causing the surrounding rock to fracture, which allows water to flow more easily. This technique is similar to the fracking method used in oil and gas extraction, though it does not involve toxic chemicals. Instead, materials like sand or ceramic particles are used to keep the cracks open, ensuring the water flows effectively. The size of the geothermal reservoir can also be expanded using directional drilling. Small-scale enhanced geothermal systems have been successfully set up in locations like Saultz-sous-Forêt in France and Landau and Insheim in Germany. Closed-loop geothermal systems, sometimes known as advanced geothermal systems, use a system of pipes buried deep underground that circulate a working fluid without directly contacting the rocks. This method offers several advantages: no need for geofluids, no requirement for the rocks to be permeable, and the ability to recirculate the working fluid without loss. A Canadian company, Evor, piloted a closed-loop system in Alberta, Canada. Although the geothermal gradient was insufficient for generating electricity, the system produced about 11,000 megawatt-hours of thermal energy during its first 2 years of operation. Like wind and solar energy, geothermal power has low operational costs, but the initial capital costs are high, with drilling costs being the biggest expense. For example, drilling a typical geothermal well in Nevada costs about $10 million for each well pair, one for extraction and one for reinjection, and can produce 4.5 megawatts of electricity. However, the failure rate for these wells is around 20%, meaning that the average cost of a successful well is about $50 million. Drilling geothermal wells is more expensive than drilling for oil and gas for several reasons. First, geothermal reservoirs are usually found in harder rock formations, such as igneous or metamorphic rock, making them more difficult to penetrate than the sedimentary rocks typically found in oil and gas fields. Additionally, geothermal rocks are often fractured, which causes vibrations that can damage drilling tools. The rocks may also contain abrasive materials like quartz or corrosive fluids, and the high heat of the reservoirs can damage electronics used in the drilling process. Finally, geothermal wells require casing that is cemented along the entire length of the well to withstand temperature changes, whereas oil and gas wells are usually only cemented at the bottom. Also, geothermal wells tend to be much wider than traditional oil or gas wells. Between the years 2013 and 2020, private investments were the biggest source of funding for renewable energy, making up about 75% of the total funding. The balance between private and public investments varies depending on the type of renewable energy technology, with some technologies being more appealing or ready for the market than others. For example, in the year 2020, geothermal energy received only 32% of its investment from private sources. In January of the year 2024, a report called Socioeconomic Impacts of Geothermal Energy Development was published by the Energy Sector Management Assistance Program, SMAP. This report highlighted the significant socioeconomic advantages of geothermal energy development, noting that it offers more benefits than wind and solar power by creating an estimated 34 jobs for every megawatt of energy produced. These jobs span multiple sectors and include opportunities for skill development through hands-on training and formal education, which strengthens the local workforce and creates more employment. The report also emphasized how geothermal energy projects work closely with local communities, improving infrastructure, offering skill-building programs, and introducing revenue-sharing models. These efforts not only help provide reliable electricity and heat, but also have the potential to boost agricultural productivity and food security. The report further discussed the focus on gender equality and social inclusion by providing job opportunities, education, and training for underrepresented groups, ensuring equal access to the benefits of geothermal development. Together, these initiatives support economic growth, increase government revenue, and contribute to more stable and diverse national economies, while also providing significant social benefits like improved health, education, and stronger communities. Geothermal energy projects go through several stages of development, each of which comes with its own risks. Many projects are abandoned during the early stages of exploration and geophysical surveys, as these stages are not suitable for traditional forms of lending. However, later stages are often funded through equity financing. One common challenge with geothermal systems occurs when they are located in areas with carbonate-rich rock formations. In these cases, the fluids used to extract heat from the earth can dissolve small pieces of rock as they move upward. When the fluids cool, the dissolved minerals, such as calcium, precipitate out and form a buildup of scale known as calcite scaling. This can reduce the flow rate and require the system to be shut down for maintenance. Geothermal energy is considered sustainable because the amount of heat we extract from the Earth is tiny compared to the planet's total heat content, which is about 100 billion times the total energy consumption worldwide in the year 2010. The Earth's heat flows are not in balance. The planet is gradually cooling over geological timescales. Extracting heat from geothermal sources does not speed up this cooling process. Wells can also be considered renewable because the extracted water is typically returned to the borehole to be reheated and reused, although it returns at a lower temperature. In many areas, using energy instead of materials has significantly reduced the environmental impact of human activities. Geothermal energy has the potential to reduce this impact even further. For instance, Iceland has enough geothermal energy to replace fossil fuels for electricity generation, as well as to heat the sidewalks in Reykjavik and eliminate the need for salting. However, it's important to consider the local effects of heat extraction. Over the course of decades, geothermal wells can lower local temperatures and water levels. The three oldest geothermal sites, at Lardorello, Wairake, and the geysers, have seen reduced output because of local depletion, as heat and water were extracted faster than they could be replenished. Reducing production and injecting water back into the wells has helped these sites recover some of their original capacity, and this strategy has been successfully implemented at some locations, allowing them to continue providing significant energy. The Wairake power station, which began operations in November of the year 1958, reached its peak output of 173 megawatts in the year 1965. However, by then, the supply of high-pressure steam was already dwindling. In the year 1982, the station's output was reduced to 157 megawatts, and in 2005, two 8-megawatt isopentane systems were added, increasing the output by about 14 megawatts. Unfortunately, detailed data were lost due to reorganization. Fluids extracted from geothermal sources often contain gases, such as carbon dioxide, hydrogen sulfide, methane, and ammonia. If these gases are released into the atmosphere, they can contribute to global warming, acid rain, and unpleasant odors. On average, existing geothermal power plants emit about 122 kilograms of carbon dioxide for every megawatt-hour of electricity produced, which is a small fraction of the emissions from fossil fuel plants. However, some geothermal plants, such as those in Turkey, emit more pollutants than gas-powered plants, especially during the initial years of operation. To address this, many geothermal plants have been equipped with emission control systems to reduce these pollutants. New technologies, like the closed-loop systems developed by EVOR, hold the promise of reducing emissions to zero. Geothermal fluids can also contain trace amounts of toxic elements such as mercury, arsenic, boron, and antimony. As the fluids cool, these chemicals can precipitate out and cause environmental harm if they are released. The modern practice of re-injecting geothermal fluids back into the Earth helps reduce this environmental impact by preventing these harmful substances from escaping into the environment. Construction of geothermal plants can sometimes affect the stability of the land. In the Reactor field, land subsidence was observed, while in Staufen im Breisgau, Germany, tectonic uplift occurred. In this case, a previously isolated anhydrite layer came into contact with water and transformed into gypsum, causing its volume to double. Additionally, enhanced geothermal systems can trigger earthquakes as part of the hydraulic fracturing process. For example, a project in Basel, Switzerland, was suspended after over 10,000 seismic events, with some measuring up to 3.4 on the Richter scale, occurred in just the first 6 days of water injection. Geothermal power production requires relatively little land and fresh water compared to other energy sources. Geothermal plants use about 3.5 square kilometers per gigawatt of electricity produced, compared to 32 square kilometers for coal plants and 12 square kilometers for wind farms. They also use just 20 liters of fresh water per megawatt hour of electricity, compared to over 1,000 liters used by nuclear, coal, or oil plants. Perpetual motion refers to the continuous movement of objects that never stops in a system without any interruptions. A perpetual motion machine is a theoretical device that can do work forever without needing an outside source of energy. However, such a machine is impossible because its existence would break the first and/or second laws of thermodynamics. These laws apply to all systems, no matter how large or small. For instance, the movement of planets and other celestial bodies may seem like perpetual motion, but they are actually affected by various forces that slowly drain their energy. These forces include solar wind, resistance from the interstellar medium, gravitational radiation, and thermal radiation. Therefore, these bodies won't keep moving forever. Machines that take energy from limited sources can't run forever because they rely on energy that is eventually used up. A common example is devices that are powered by ocean currents. The energy from these currents ultimately comes from the sun, which itself will burn out one day. In the year 2016, scientists discovered new forms of matter called time crystals. These time crystals show continuous motion on a tiny scale, with the atoms moving in a repetitive pattern. This satisfies the literal definition of perpetual motion. However, they do not function as perpetual motion machines in the traditional sense, nor do they violate thermodynamic laws. This is because they exist in their quantum ground state, meaning no energy can be taken from them. They move without using energy. The concept of perpetual motion machines goes back to the Middle Ages. For many years, it was unclear whether such machines could exist. However, the development of modern thermodynamics showed that they are impossible. Still, many people have tried to create these machines, even in modern times. Today, some inventors call their ideas over-unity devices instead of perpetual motion machines. There is a broad scientific agreement that perpetual motion in a closed system breaks at least one of the laws of thermodynamics. The first law, also known as the law of conservation of energy, states that energy cannot be created or destroyed. The second law has several formulations, but one way to think of it is that heat naturally flows from hotter to cooler areas. It also tells us that no engine can be more efficient than a Carnot engine working between the same two temperatures. In a closed system, energy cannot be created from nothing, which is the principle of conservation of energy. Because of this, the efficiency of any engine, meaning how much work it produces compared to the energy it consumes, can never be more than 1. The power output of heat engines is always less than the heat energy input. The leftover heat is lost to the surroundings. The maximum possible efficiency of a heat engine is given by the Carnot efficiency, which is always less than 1. Real-world heat engines are even less efficient than the Carnot engine due to factors like friction and the speed of processes. Other types of engines, like those converting mechanical energy into electromagnetic energy, cannot reach 100% efficiency either. This is because it's impossible to design a system that doesn't lose energy in some form. Some machines, though, seem to break the laws of thermodynamics because they use unconventional energy sources. These machines, like clocks or other low-power devices, might appear to run without a clear energy source. For example, some machines are powered by differences in air pressure or temperature between night and day. They seem to defy the laws, but they really just use hidden energy sources, so they are not true perpetual motion machines. Machines that use long-lasting energy sources, like ocean currents, will eventually stop when their energy runs out. These are not perpetual motion machines because they rely on external energy sources, not on isolated systems. Perpetual motion machines are often categorized by the specific thermodynamic law they break. A perpetual motion machine of the first kind creates work without any energy input, breaking the law of conservation of energy. A perpetual motion machine of the second kind spontaneously turns heat into mechanical work. While this doesn't break the first law of thermodynamics, it violates the second law. This machine would involve only one heat source, which would cool down without transferring heat to a cooler place, something that the second law says is impossible. A perpetual motion machine of the third kind is one that eliminates all friction and other forces that cause energy loss, allowing it to move forever due to its mass inertia. However, this is impossible because it's impossible to completely eliminate energy dissipation, even in the best systems. The term epistemic impossibility describes things that cannot happen according to our current understanding of physical laws. This is the kind of impossibility that applies to perpetual motion in closed systems. The conservation of energy is a fundamental principle, and its mathematical foundations are very strong. In the year 1915, mathematician Emmy Noether proved a theorem showing that any conservation law can be traced back to a continuous symmetry in the physical system. In the case of energy conservation, this symmetry is time invariance, meaning that the laws of physics don't change over time. If energy conservation could be violated, it would mean that the very foundations of physics would need to change. Scientists have long been curious about whether the laws of physics stay the same over time. To find out, they use powerful telescopes to look at stars far away in the universe, trying to see if stars from billions of years ago were like the ones we see today. By using different tools, such as spectroscopy, which helps study light, measuring the speed of light in the past, and other similar methods, scientists have shown that the laws of physics have stayed nearly the same throughout all observable time, which spans billions of years. The laws of thermodynamics, which explain how energy works, are so firmly established that any idea for a perpetual motion machine, one that runs forever without an energy source, gets quickly rejected by scientists. When someone proposes a new design for such a machine, physicists know right away that it cannot work, but they still take the time to explain why it won't work. The challenge is not in proving it doesn't work, but in explaining the failure. The complexity and value of this explanation depend on the details of the design. Often, these designs come from physicists' own thought experiments and can help us better understand certain concepts in physics. For instance, in the year 1900, a physicist named Gabriel Lippmann imagined a machine that could potentially work forever, which he called the Brownian ratchet. It wasn't until 12 years later, in 1912, that another scientist, Marian Smoluchowski, explained why the machine couldn't work. During those 12 years, scientists didn't think it was possible for the machine to work. They simply didn't know exactly how it would fail. In the mid-19th century, the scientist Henry Dirks looked into the history of people trying to create perpetual motion machines. He wrote a harsh criticism of those who kept trying to make what he believed to be an impossible invention. Many of the ideas used in perpetual motion machines are not new. In fact, some of these ideas were first mentioned in the year 1670 by John Wilkins, the Bishop of Chester, who was also a member of the Royal Society. He suggested 3 possible sources of energy for perpetual motion machines: chemical extractions, magnetical virtues, and the natural affection of gravity. Magnets have always fascinated inventors because they can influence motion without any visible source of energy. One of the earliest ideas for a magnetic motor came from Wilkins, and it has been copied many times since. His design involved a ramp with a magnet at the top, which would pull a metal ball up the ramp. Below the magnet, there was supposed to be a small hole through which the ball would fall to return to the bottom, where it would be lifted again by a flap to go back up. However, if the magnet is strong enough to pull the ball up the ramp, it's not weak enough to let gravity pull the ball through the hole. More modern versions try to solve this by using a series of ramps and magnets, passing the ball from one to the other, but the basic problem still remains unsolved. Gravity, like magnets, acts at a distance without any obvious energy source. However, to get energy from gravity, like when an object falls and turns into kinetic energy, we first have to put energy in, such as lifting the object. Additionally, some energy is always lost in the process. A well-known example of a gravity-based perpetual motion machine is Bhaskara's wheel, created in the 12th century. This machine used weights attached to a wheel. The idea was that the weights would move farther from the wheel's center during one half of the wheel's rotation and then move closer to the center on the other half. The further weights were thought to create enough force to keep the wheel turning forever. However, because the side with the further weights had fewer of them than the other side, the forces balanced out and the wheel stopped moving after a short time. Another idea was to create a machine where motion happens in a frictionless environment. This would use magnets or electromagnetic forces to levitate an object, allowing it to spin without touching anything. However, this type of machine is impractical. While the object might spin freely, it cannot do any useful work. Work requires an object to cause motion in something else, which would bring friction into the equation. Also, creating a perfect vacuum where no air molecules remain is impossible, as both the container and the object would slowly start to break down. Another attempt to create perpetual motion involves using heat to generate work. This idea, dating back to Maxwell's demon, a thought experiment, suggests that only molecules moving fast enough and in the right direction would be allowed through a trapdoor. In a Brownian ratchet, forces would turn the ratchet in one direction, but not the other. However, these machines typically fail in 2 ways. Either keeping the movement in one direction takes more energy than is gained, or the unidirectionality is an illusion, with occasional big violations making up for small, regular failures. Some proposed perpetual motion machines misunderstand buoyancy. These machines try to use air or fluid to do work, but to push air down in a liquid requires the same amount of energy as lifting the liquid up against gravity. For example, one idea uses 2 chambers with pistons and a mechanism to push air into the bottom chamber. The bottom chamber becomes buoyant and rises, but the work required to push the air down cannot generate enough energy to keep the machine working. A perpetual motion machine is a concept that describes a device capable of running indefinitely without requiring any energy input. However, this idea only makes sense when applied to a closed, isolated system with fixed properties. But in reality, isolated systems don't exist due to factors like quantum uncertainty, which complicates the idea of perpetual motion. Therefore, when discussing perpetual motion here, it's better to think of it as a perpetual motion machine, a device that operates continuously to perform a task, whether mechanically, electrically, or electronically. While perpetual motion machines are often discussed, especially in the context of technical designs or ideas, further examination reveals that these systems usually end up consuming some sort of natural energy or latent force. This could include things like the phase changes of water, temperature differences in fluids, or other small energy sources. In most cases, these devices cannot sustain operation indefinitely. Essentially, it's impossible to extract usable work from them in the long run. The drinking bird toy works by taking advantage of small temperature differences in the surrounding air and the process of evaporation. It continues to run until the water in the toy evaporates completely. A water pump powered by capillary action relies on small temperature gradients and pressure differences caused by water vapor. Originally, it was thought that capillary action would keep the water flowing, but in practice, the liquid gets stuck in the tube due to forces that prevent it from releasing back into the container. Therefore, the flow is not endless. A Crookes radiometer contains a small propeller inside a partial vacuum. The propeller moves due to temperature differences caused by light. Solar-powered motors capture tiny amounts of energy from sunlight and use it to operate. These devices are powered by natural electromagnetic radiation, but can't produce energy beyond what is supplied. Certain types of clocks, like Cox's timepiece and the Beverly clock, are driven by changes in air pressure, where moving air provides energy that was originally created through some other force. A heat pump is another example of a system with a coefficient of performance, COP, above 1. This means it moves more energy as heat than it consumes as work, but still, it doesn't create free energy. The Atmos clock winds itself using the changing pressure of ethyl chloride, a chemical which fluctuates with temperature. There are devices that could theoretically be powered by nuclear reactions or by the slow decay of radioactive materials, allowing them to operate for hundreds or even thousands of years. Flywheel energy storage systems can store energy for long periods. Modern flywheels, for instance, can continue spinning for years when there's no external force acting on them. In space, objects like planets, moons, and even stars continue to rotate for long periods because they lose energy very slowly, even though they are in a vacuum. On Earth, tidal forces between the Moon and the Earth dissipate about 3.75 terawatts of energy every second. In certain quantum systems, like superfluidity and superconductivity, motion can occur with minimal friction, allowing for movement that seems almost perpetual. However, once the system reaches balance, the motion halts. Similarly, effects like superfluids climbing up container walls happen through normal capillary action. Some thought experiments have suggested that perpetual motion could be possible using understood physical processes. However, these ideas always have flaws when all aspects of physics are taken into account. For example, Maxwell's demon was a thought experiment aimed at challenging the second law of thermodynamics. It suggested a creature that could sort fast-moving and slow-moving molecules, theoretically extracting useful energy. However, further analysis revealed that any such system would still increase overall entropy, which makes it impossible to implement. The Brownian ratchet imagined a device where Brownian motion, random movement of particles, would cause a paddle to turn in one direction only. But when scientists considered how a physical ratchet would work on the molecular scale, it was clear that Brownian motion would also affect the ratchet in unpredictable ways, making it ineffective. Zero-point energy refers to the background energy that exists even in empty space, suggested by some quantum theories. Though some have hoped to harness this energy for useful work, no reliable method for doing so has ever been found, and the scientific community generally dismisses such claims as pseudoscience. The ellipsoid paradox involves a thought experiment where radiation inside a perfectly reflective cavity leads to strange behavior between two black bodies. However, this paradox is resolved when the finite size of the black bodies is considered rather than treating them as point sources. Despite these ideas being widely dismissed as pseudoscience, some conspiracy theories claim that perpetual motion machines are being hidden by corporations or governments to prevent the discovery of cheap, unlimited energy sources that could disrupt the global economy. Fusion power is a type of energy generation that aims to create electricity by harnessing the heat produced from nuclear fusion reactions. In a fusion process, two lighter atomic nuclei join together to form a heavier nucleus, releasing energy in the process. The machines built to capture this energy are known as fusion reactors. Research into fusion reactors started in the 1940s, but as of the year 2025, no fusion reactor has produced more energy than it consumes, though there have been experiments where energy-producing reactions have been achieved. Fusion requires fuel in the form of plasma, a state where matter is so hot that the electrons are stripped from their atoms. The fusion process also needs the right environment, including high temperatures, enough pressure, and a certain amount of time for the particles to stay in the confined area. The set of conditions that allows a fusion system to produce power is called the Lawson criterion. In stars, the most common fuel for fusion is the lightest type of hydrogen, known as protium, and gravity helps provide the necessary conditions for fusion. Proposed fusion reactors would use heavier forms of hydrogen called deuterium and tritium for fusion, because these elements are easier to fuse and meet the Lawson criterion more readily. When these two elements fuse, they produce a helium atom and a high-energy neutron. Most fusion reactor designs aim to heat the fuel to about 100 million kelvins, but getting the correct pressure and time for confinement has proven very difficult. For fusion reactors to be useful for energy production, they need to create much more energy than they use, not just reach break-even. Fusion fuel is incredibly dense, with 10 million times more energy per unit of fuel than coal, but tritium is very rare on Earth, as it only has a half-life of around 12.5 years. This means that during fusion reactor operations, lithium blankets will need to be used to generate tritium through neutron reactions. Nuclear fusion has several potential benefits over nuclear fission, such as producing far less high-level waste and being safer. However, one challenge of fusion is dealing with the neutron radiation produced during the reactions, which can damage the reactor, especially the first wall. Fusion research is mostly divided into two types: magnetic confinement and inertial confinement. Magnetic confinement systems have been studied since the 1940s, initially with designs like the Z-pinch, stellarator, and magnetic mirror. The tokamak design, developed and tested in the Soviet Union in the late 1960s, became the most widely researched approach for magnetic confinement. Inertial confinement, which began development in the 1970s, focuses on using lasers to compress and heat fuel to start fusion. Today, the largest fusion projects in the world are the ITER tokamak in France and the National Ignition Facility, NIF, laser in the United States. Many researchers and companies are also exploring new, potentially less expensive fusion designs, including magnetized target fusion and new versions of the stellarator. When scientists talk about a fusion experiment or a fusion device, they are referring to the various technologies used to study and develop fusion energy. Not all of these devices are capable of or routinely used to create thermonuclear reactions. The term fusion reactor can mean either the experimental devices mentioned above or a theoretical power-producing device in a power plant, which would require additional components like a breeding blanket to generate fuel and a heat engine to convert the energy into electricity. Fusion reactions happen when two atomic nuclei come close enough together for long enough that the nuclear force pulling them together is stronger than the electrostatic force that pushes them apart, causing them to fuse into a heavier nucleus. For heavier elements than iron, this process requires an input of energy, as the repulsive force between the protons in these larger nuclei is greater. However, for lighter elements like hydrogen, fusion releases energy. Since hydrogen atoms have only one proton, they require less effort to fuse, and this fusion process releases the most energy. Additionally, hydrogen is easier to fully ionize because it only has one electron. The electrostatic repulsion between the nuclei is stronger at greater distances than the strong force that pulls them together, which operates over extremely short ranges. To start fusion, the fuel atoms must be heated or accelerated with enough kinetic energy to overcome this electrostatic barrier and get close enough for the strong force to take over. The amount of energy needed to do this is known as the Coulomb barrier. Atoms can be heated to very high temperatures or accelerated in a particle accelerator to gain enough energy. When atoms are heated beyond a certain point, they lose their electrons, becoming ions. This process creates plasma, a hot cloud of bare atomic nuclei and free electrons that used to be bound to them. Plasmas conduct electricity and can be controlled using magnetic fields, which is why many fusion devices use magnetic fields to keep the plasma in place. The Lawson criterion helps determine the energy balance between the energy generated by fusion reactions and the energy lost to the environment. For fusion to be a viable energy source, the system must produce more energy than it loses. The rate at which fusion occurs, and therefore the amount of fusion power, depends on both the temperature and the density of the plasma. Plasma loses energy through two main ways: conduction and radiation. Conduction happens when ions, electrons, or neutral particles collide with other substances, usually the surface of the device, and transfer part of their energy to those atoms. The rate of conduction is also influenced by the temperature and density. Radiation, on the other hand, is energy that escapes the plasma as light. Like conduction, radiation increases as the temperature rises and as the mass of the ions gets bigger. For fusion power systems to work, the rate at which fusion happens must be higher than the energy that is lost through conduction and radiation. The Lawson criterion is a rule that says a machine holding a plasma, where the particles are in a stable state and neutral in charge, must produce enough energy to overcome its own energy losses. The amount of energy released in a specific volume depends on the temperature, which affects how quickly reactions happen between particles, the density of those particles within the volume, and the confinement time, which is the amount of time the energy stays inside that volume. This combination of factors is called the triple product: plasma density, temperature, and confinement time. In magnetic confinement systems, the density is very low, similar to a good vacuum. For example, in the ITER machine, the fuel density is around 1.0 times 10 to the power of 19 particles per cubic meter, which is about 1/1,000,000th of the density of the air we breathe. To make up for this, either the temperature or the confinement time must be increased. Fusion-relevant temperatures were first achieved in the early 1970s through different heating methods. As of 2019, the main challenge for these machines is the confinement time. Plasmas in strong magnetic fields can become unstable, and these instabilities need to be controlled to achieve useful fusion durations. One way to deal with this is to simply make the reactor larger, which reduces the loss of energy due to classical diffusion. This is one reason why the ITER machine is so large. In comparison, inertial confinement systems reach useful values of the triple product through higher density, but with shorter confinement times. In the National Ignition Facility, NIF, the initial hydrogen fuel has a density less than water, but it is compressed to about 100 times the density of lead. Under these conditions, fusion happens so rapidly that the fuel fuses in the microseconds it takes for the heat from the reactions to blow the fuel apart. Though the NIF is large, this size is mainly due to its design, not because of the fusion process itself. Various ideas have been suggested for how to capture the energy produced by fusion. The simplest idea is to heat a fluid. The most common fusion reaction, deuterium-tritium, DT, releases much of its energy as high-speed neutrons. Because neutrons have no electric charge, they are not affected by the magnetic fields that contain the plasma. In most designs, the neutrons are captured in a thick blanket made of lithium around the reactor core. When these high-energy neutrons strike the blanket, it heats up. This heat is then carried away by a working fluid, which can drive a turbine to generate electricity. Another design idea is to use the neutrons to create more nuclear fuel from nuclear waste, known as a fission-fusion hybrid. In these systems, the fission reactions help increase the power output, and the energy is extracted using the same methods as in traditional nuclear reactors. Some fusion designs use other fuels, like the proton-boron fusion reaction, which releases more of its energy as charged particles. In these cases, it is possible to capture power directly by using systems that move these charged particles. A method for this, called direct energy conversion, was developed at the Lawrence Livermore National Laboratory in the 1980s. This method has demonstrated an energy capture efficiency of 48%. Plasma is a special kind of gas that has been charged, meaning its particles are split into positive and negative parts. This charged gas can carry electricity. When we look at it in large amounts, we use a set of scientific rules to explain how it behaves, which combines the study of how fluids move and how electricity and magnets interact. In fusion, several important features of plasma are used to help create energy. Plasma naturally organizes itself to carry electric and magnetic fields. Its movement generates fields that can trap the plasma, keeping it in place. Plasma can also make its own magnetic field. This can push away an outside magnetic field, making it diamagnetic. When plasma moves from an area of low density to one with higher density, magnetic mirrors can reflect it back and forth, helping to contain it. One of the most studied and funded ways to control plasma for fusion energy is the tokamak method. This technique drives very hot plasma around in a donut-shaped magnetic field with a current running inside it. Once fully built, the International Thermonuclear Experimental Reactor, ITER, will be the largest tokamak in the world. As of September 2018, about 226 tokamaks had been planned, decommissioned, or were in operation across the globe. Another variation is the spherical tokamak, which has a round shape instead of the usual donut shape. It is also known as a spherical torus. There is also the stellarator, which creates twisted loops of hot plasma. It tries to make the plasma follow a natural twisted path using external magnets. The stellarator was first developed by Lyman Spitzer in the year 1950 and has since evolved into 4 types: torsatron, heliotron, heliac, and helios. The largest stellarator in the world today is the Wendelstein 7X, based in Germany. Some other designs, like internal rings, create twisted plasma by using conductors inside the plasma. Early tests showed that energy loss from the conductors was too fast for fusion to be practical, but newer experiments, such as the levitated dipole experiment, have improved this by using superconducting rings that float inside the reactor chamber. A magnetic mirror reflects plasma back and forth in a straight line. This concept was developed by Richard F. Post and his team in the 1960s. Although the US government tried many designs of magnetic mirrors in the 70s and 80s, it was determined that they probably wouldn't be useful for producing energy. Another approach is the bumpy torus, which arranges several magnetic mirrors in a circular shape. This helps keep the plasma from leaking out, allowing for higher plasma pressure. One such experiment, the Elmo bumpy torus, was tested in the 1970s at Oak Ridge National Laboratory in the United States. The field-reversed configuration traps plasma in a stable structure created by its own internal magnetic field. A similar device, called a spheromac, uses a self-generated magnetic field to keep plasma in place. Unlike a field-reversed configuration, a spheromac has both toroidal and poloidal magnetic fields. Another design, the dynamomac, is a spheromac that is made and maintained using a continuous magnetic field. The reversed field pinch is a method where plasma moves inside a ring with an internal magnetic field that reverses direction as you move outward from the center. In some fusion methods, lasers are used to compress fuel. In the indirect drive method, lasers heat a special container, called a hohlraum, which then emits X-rays that compress the fuel. The largest system using this method is the National Ignition Facility, with another large system being the laser megajoule. In the direct drive method, lasers are used directly on the fuel pellet. Notable experiments in this area have been done at the Laboratory for Laser Energetics and the Gecko 12 facility. Fast ignition involves using two laser pulses. The first compresses the fuel and the second ignites it. However, by the year 2019, this method had lost favor for energy production. Magneto-inertial fusion, or magnetized liner inertial fusion, combines lasers with a magnetic pinch to compress plasma for fusion. Ion beams are another option to replace lasers for heating fuel. They have mass, unlike lasers, and thus carry momentum. However, as of the year 2019, it seems unlikely that ion beams can be focused accurately enough for practical use. The Z-machine uses an electric current passed through thin tungsten wires to generate X-rays, which then compress a fuel capsule, much like the indirect drive approach. The Z-pinch sends a current through plasma in the Z direction. This current creates a magnetic field that compresses the plasma, but it has limits that make it difficult to use for practical fusion. The largest machine built using this method was the UK's Zeta, which was the last significant experiment of its kind before scientists moved toward tokamaks. The theta pinch is similar, but it sends a current around the outside of the plasma. This also creates a magnetic field, but in a different direction. Early experiments with the Scylla device showed that it could achieve fusion, but further tests showed that it wasn't suitable for power production. A method called sheared flow stabilized Z-pinch was investigated at the University of Washington. This involves stabilizing the Z-pinch by accelerating neutral gas along the axis of the pinch. In the year 2017, an entrepreneur named Benj Conway, along with physicists Brian Nelson and Yuri Shumlak, co-founded Zap Energy to work on commercializing this technology for producing energy. Screw pinch. This method combines two techniques, the theta pinch and the Z pinch, to improve the stability of plasma during fusion experiments. Polywell. This approach tries to combine magnetic fields with electrostatic forces to reduce energy losses that occur in the magnetic cage used to hold the plasma. Magnetized target fusion. This method traps hot plasma using magnetic fields and compresses it using pressure from inertia. Examples include the LANL FRXL machine, general fusion, which uses a piston and a liquid metal liner for compression, and hyperjet fusion, which uses plasma jets and a plasma liner. Uncontrolled fusion. Fusion reactions have been started by humans through the use of uncontrolled fission explosions, such as nuclear bombs, to trigger fusion. Early ideas for generating fusion power included using these explosions as a way to start fusion reactions. Muon-catalyzed fusion. This method involves replacing the usual electrons in hydrogen isotopes with muons, which are heavier particles with the same electric charge. Their extra mass helps to compress the hydrogen nuclei enough to trigger fusion. However, as of the year 2007, it requires more energy to produce muons than can be gained from the fusion reactions they catalyze. Lattice confinement. Fusion. In this type of fusion, deuterium-saturated metals are exposed to gamma radiation or ion beams. Unlike other fusion methods, which use high-temperature plasma, Lattice confinement fusion avoids such extreme conditions. It uses the structure of the metal to help contain the hydrogen isotopes and facilitate fusion. All of these fusion methods currently require more energy than they can produce, making them inefficient for power generation. Fusor. In a fusor, an electric field is used to heat ions to the temperatures needed for fusion. The device typically uses two spherical cages, one inside the other, placed in a vacuum. Despite their simplicity, these machines are not considered practical for producing net power due to high energy losses from conduction and radiation. Still, they are simple enough that some amateur enthusiasts have managed to achieve fusion reactions. Colliding beam. Fusion. This method involves firing beams of high-energy particles at each other or at a target to create fusion reactions. It was used in the 1970s and 80s to study fusion reaction cross-sections. However, it is not a practical approach for power generation, as keeping the beams focused and energetic requires more energy than can be obtained from the fusion reactions themselves. Deep reinforcement learning for tokamaks. A deep reinforcement learning system has been used to control the operation of a tokamak-based fusion reactor. This system can adjust the magnetic coils to manage the plasma effectively, continuously fine-tuning the reactor's behavior. In 2014, Google partnered with the fusion company TAE Technologies to help control the joint European torus reactor and predict plasma behavior. DeepMind, another Google project, has also developed a similar system for controlling plasma in the tokamak, a configuration variable reactor. Electrostatic heating. In this method, an electric field is used to heat charged particles such as ions or electrons, increasing their energy. Neutral beam injection. In this technique, hydrogen is first ionized and then accelerated by an electric field to form a charged beam. The beam is directed at neutral hydrogen gas, which then interacts with the plasma. This energy transfer heats the plasma and refuels it in one process. The remaining charged particles are diverted to cooling systems. Radio frequency heating. This method uses radio waves to heat the plasma, similar to how a microwave oven works. Known as electron cyclotron resonance heating, it uses devices such as gyrotrons to transfer energy into the plasma. Magnetic reconnection. As plasma becomes dense, its electromagnetic properties can change, leading to a phenomenon known as magnetic reconnection. This process rapidly releases energy, heating the plasma and aiding fusion reactions. Up to 45% of the magnetic field energy can be converted into heat for the plasma ions. Magnetic oscillations. In this method, alternating electric currents are passed through magnetic coils to heat the plasma inside a magnetic wall, helping to maintain the necessary temperature for fusion. Antiproton annihilation. Injecting antiprotons into a fusion fuel mass could potentially induce thermonuclear reactions. This idea was explored as a possible method for spacecraft propulsion, specifically through antimatter-catalyzed nuclear pulse propulsion. Researchers at Pennsylvania State University investigated this concept as part of the AIM-STAR project. Fusion reactor diagnostics. The diagnostic systems for a fusion reactor are highly complex and varied. For a commercial fusion power plant, these systems will be less complicated than those of a research reactor because real-time monitoring and control systems will have been perfected. However, operating a commercial fusion reactor will be much more challenging due to the harsh environment, which includes higher plasma temperatures and more intense neutron radiation. Monitoring systems will need to measure and separate gases like helium and impurities and track the state of tritium breeding systems like a liquid lithium liner used in some reactors. Flux loop. A wire loop is placed inside a magnetic field. As the magnetic field passes through the loop, it creates an electric current. This current helps measure the total magnetic flux passing through the loop. This technique has been used in various experimental fusion devices, including the National Compact Stellarator experiment, the Polywell, and the LDX machines. Another tool used in fusion research is the Langmuir probe, which is a metal object inserted into a plasma. A voltage is applied to the probe, creating a voltage difference between it and the surrounding plasma. The probe collects charged particles, producing a current. As the voltage changes, the current also changes, which can be graphed as an IV curve. This curve is useful for determining important plasma properties, such as its local density, potential, and temperature. Thomson scattering. Light scattered by the plasma can help scientists understand the behavior of the plasma, including its density and temperature. This method is commonly used in inertial confinement fusion, ICF systems, tokamaks, and fusers. In ICF experiments, a second beam is fired into a gold foil near the target. This creates X-rays that pass through the plasma. In tokamaks, mirrors and detectors can be used to reflect and measure the light scattered from the plasma. Neutron detectors. Different types of neutron detectors can measure the rate at which neutrons are produced in a fusion reaction. These detectors provide important data about the fusion process. X-ray detectors. When particles in a plasma change speed, they emit various types of radiation, including visible light, infrared, IR, ultraviolet, UV, and X-rays. If a particle's speed change is caused by deflection in a magnetic field, the radiation emitted is known as cyclotron radiation at low speeds and synchrotron radiation at high speeds. If the speed change is caused by a collision with another particle, the plasma emits X-rays in a process called Bremsstrahlung radiation. Neutron blankets. Neutron blankets are materials that absorb neutrons produced during fusion. The absorption of neutrons heats the blanket, and this heat can be used to generate power. For example, heat can be transferred to a working fluid, which turns into steam and drives turbines to generate electricity. Neutron blankets also have the potential to regenerate spent nuclear fuel and produce tritium. This can be done using a breeder blanket made of liquid lithium or a helium-cooled pebble bed made of lithium-bearing ceramic pebbles. Direct conversion. In this process, the kinetic energy of a particle is converted directly into electricity. This idea was first proposed by Richard F. Post in the late 1960s in conjunction with magnetic mirrors. It has also been suggested for use in field-reversed configurations and dense plasma focus devices. The method works by converting much of the random energy of fusion products into directed motion. The charged particles are then collected on electrodes at various electrical potentials. This approach has shown an experimental efficiency of 48%. Traveling wave tubes. In this process, charged helium atoms that are produced by fusion reactions are passed through a tube with a coil of wire wrapped around it. The atoms move through the tube at several megavolts of energy, and their motion induces an electric current in the wire. Confinement. Confinement refers to the conditions needed to keep plasma dense and hot enough for fusion to occur. Key principles of confinement include equilibrium. The forces acting on the plasma must be balanced. However, in inertial confinement, fusion must happen quickly enough to prevent the plasma from dispersing. Stability. The plasma must be stable so that disturbances do not cause it to break apart. Transport or conduction. Plasma must not lose material too quickly. If it does, the fusion process can be disrupted. Loss of material can happen if it moves into different areas or is conducted through a solid or liquid. To achieve self-sustaining fusion, some of the energy released by the fusion reaction must be used to heat the incoming fuel and maintain the necessary conditions for fusion to continue. Magnetic mirror effect. The magnetic mirror effect occurs when a particle moves along a magnetic field line and enters a region with a stronger magnetic field, causing the particle to reflect back. Several fusion devices use this principle, such as the magnetic mirror machines built at the Lawrence Livermore National Laboratory, LLNL, from the 1960s to the 1980s. Other devices, like magnetic bottles and the biconic cusp, also use this effect. Magnetic mirrors are simpler to construct and maintain compared to ring-shaped designs, and they make it easier to collect energy through direct conversion. However, poor confinement has led to the abandonment of magnetic mirror devices in most cases, except for the Polywell design. Magnetic loops. Magnetic loops bend the magnetic field lines into shapes like circles or nested toroidal surfaces. Some of the most advanced systems using magnetic loops are the tokamak, the stellarator, and the reversed field pinch. Compact toroids, like the field reverse configuration and the spheromak, aim to combine the benefits of toroidal magnetic surfaces with a more mechanically simple, smaller confinement area. These devices are not shaped like a ring, which offers certain advantages in terms of design and performance. Inertial confinement is a method where plasma is heated and contained by causing it to collapse very quickly. This collapse, or implosion, is achieved by using intense energy, either from a direct laser blast, a secondary X-ray blast, or heavy beams. The surrounding shell of fuel is squeezed to about 30 times its normal density by these energetic beams. While direct drive, where the laser hits the shell directly, could, in theory, be efficient, it hasn't worked well yet because the energy isn't uniformly distributed. In indirect drive, beams are used to heat the shell, making it give off X-rays, which then cause the fuel pellet to implode. Although lasers are most commonly used, other types of beams, like ion and electron beams, have also been explored for this purpose. In another fusion approach called electrostatic confinement, electric fields are used. One well-known device that uses this method is the fusor. It has a cathode inside a cage made of an anode wire. Positive ions move toward the negative inner cage, getting heated by the electric field along the way. If the ions miss the cage, they may collide and fuse. However, ions usually hit the cathode, which results in a loss of energy due to heat conduction, making the process inefficient. Fusion rates in fusors are low because other factors, like light radiation, cause energy losses. There have been ideas proposed to address these issues, such as using a non-neutral cloud to generate the field instead of the cage. These designs include devices like the plasma oscillating device, the magnetically shielded grid, the penning trap, the Polywell, and the F1 cathode driver. The main fuels considered for fusion power are two isotopes of hydrogen, deuterium and tritium. Deuterium is found abundantly on Earth, especially in semi-heavy water, and was even co-produced at hydroelectric power stations in the past. Tritium, however, has a short half-life of 12 years and must be artificially produced. Fusion reactors would likely use a breeding blanket made of lithium to help produce tritium. Helium-3, another possible fuel, is a more speculative option, as it must either be mined from other planets or produced through other nuclear reactions. There is also a possible fusion reaction involving protium and boron-11, but this is highly theoretical and reduces neutron radiation. Deuterium is a naturally occurring isotope of hydrogen and is easy to obtain. Because the hydrogen isotopes have such a large difference in mass, they are easier to separate than uranium, which is much more difficult to enrich. Tritium, on the other hand, is rare and hard to store or produce due to its short half-life. As a result, reactors using deuterium and tritium require tritium to be bred from lithium. The DT, deuterium-tritium, fusion reaction is the most widely studied because it yields the highest energy. The reaction involving lithium-6 is exothermic, meaning it releases energy, while the reaction with lithium-7 absorbs energy but doesn't consume neutrons. To maintain a consistent neutron supply, reactions involving materials like beryllium and lead are necessary. Most fusion reactors use lithium breeding blankets that are enriched with lithium-6, since natural lithium is mostly lithium-7, which is not as effective at producing tritium. However, there are several challenges with DT fusion power. One issue is that the neutrons produced can cause activation of the reactor materials, making them radioactive. Around 80% of the energy in a DT reaction is carried away by neutrons, limiting the possibility of directly converting this energy into electricity. Additionally, because tritium is radioactive, it could potentially leak from reactors, raising concerns about environmental impact. In fact, estimates suggest that tritium leakage could lead to significant environmental radioactivity. The neutron flux in a DT fusion reactor is expected to be about 100 times higher than in traditional fission reactors, which creates significant design challenges for materials used in the reactor. After a series of DT fusion tests at the Joint European Torus, JET, the vacuum vessel became so radioactive that it needed to be handled remotely for an entire year. In practical fusion reactors, the neutrons produced would interact with lithium in a breeding blanket made of lithium ceramic pebbles, or liquid lithium, generating tritium. The energy from the neutrons would then be transferred to the lithium, which would drive electricity production. This lithium blanket also protects the outer parts of the reactor from the high neutron flux. In newer designs, such as the advanced tokamak, lithium is used inside the reactor core as a crucial design feature. The plasma in the core directly interacts with the lithium, preventing a problem known as recycling that had been an issue before. This design was successfully tested in the lithium tokamak experiment. Fusing two deuterium atoms is one of the simpler fusion reactions. This process has two possible outcomes that happen with almost the same likelihood. The best energy level to start this reaction is 15,000 electron volts, which is just a little higher than the energy needed for the deuterium-tritium DT reaction. The first outcome creates tritium, meaning a deuterium-deuterium DD fusion reactor is not free of tritium, even though it doesn't need an outside supply of tritium or lithium. If the tritium is not removed quickly, most of it gets used up inside the reactor, which reduces the need to handle tritium. However, this results in the creation of more neutrons with higher energy. Neutrons produced in the second outcome of the DD reaction have an energy of only about 2.5 million electron volts, or 0.393 picojoules, while the neutrons from the DT reaction have an energy of 14,100,000 electron volts, or 2.26 picojoules. This difference means that more isotopes are produced and materials experience more damage. If the tritium is removed quickly and replaced with helium-3, the fuel cycle is called tritium-suppressed fusion. The removed tritium decays into helium-3 with a half-life of 12.5 years. By recycling this decay product back into the reactor, the system does not need materials that are resistant to fast neutrons. If we assume that all the tritium is burned up, the amount of energy carried away by neutrons would decrease by about 18%. The main advantage of the DD fuel cycle is that it does not require the breeding of tritium. Other benefits include no dependence on lithium supplies and a somewhat gentler neutron spectrum. The downside, however, is that the energy confinement time, the time energy stays trapped in the system, needs to be 30 times longer than for the DT reaction. Also, the power produced at the same pressure and volume is 68 times less. If the tritium is completely removed and the helium-3 is recycled, only about 6% of the fusion energy is carried by neutrons. This tritium-suppressed DD fusion would require the energy confinement to be 10 times longer than the DT process, and the plasma temperature would need to be twice as high. Another approach for future controlled fusion power uses helium-3. This reaction results in helium-4 and a high-energy proton. Like the proton-boron fusion fuel cycle, most of the energy from this reaction is released as charged particles, which helps reduce the activation of the reactor housing and could make energy harvesting more efficient through different methods. However, DD reactions still produce many neutrons, making proton-boron the preferred choice for aneutronic fusion. Aneutronic fusion, which avoids the production of neutrons, also significantly reduces material and non-proliferation issues. Theoretically, helium-3 is the most reactive fuel for aneutronic fusion, But getting enough helium-3 would require large-scale mining from places like the Moon or the atmospheres of planets like Uranus or Saturn. This makes it less practical. Instead, the most promising fuel for fusion without neutrons might be fusing protium, the most common form of hydrogen, with boron. This reaction doesn't produce neutrons, but creates energetic alpha, helium particles. These particles' energy can be converted directly into electricity. Side reactions would likely produce only a small number of neutrons, carrying about 0.1% of the energy, which significantly reduces neutron scattering and minimizes material damage. The best temperature for this reaction is about 123,000 electron volts, which is nearly 10 times higher than the temperature required for pure hydrogen fusion. The energy confinement needed for this process must be 500 times better than what is required for the DT reaction, and the power density is 2,500 times lower than for DT. However, per unit mass of fuel, this is still much higher than the energy produced by nuclear fission reactors. Because the tokamak and laser pellet fusion methods aren't very efficient at confining energy, most ideas for aneutronic fusion use very different confinement techniques, such as the polywell or dense plasma focus. In 2013, a research team led by Christine Lebon at the École Polytechnique set a new record for proton-boron fusion with an estimated 80 million fusion reactions during a 1.5 nanosecond laser shot, 100 times more than previous experiments. The stability of materials used in fusion reactors is a major concern. Materials must survive the extreme temperatures and neutron bombardment inside a fusion reactor. The main challenges involve the conditions created by the plasma, the damage caused to the reactor walls by neutrons, and how the plasma interacts with the wall surfaces. To recycle hydrogen efficiently and control the amount of tritium, it is crucial to reduce hydrogen permeability in materials. The best candidates for stable materials are those with the lowest ability to absorb and spread hydrogen, like certain pure metals, including tungsten and beryllium, and compounds like carbides, dense oxides, and nitrides. Research has shown that the technique used to prepare these materials is just as important as the materials themselves. One promising method is to create a protective layer on the surface by oxidizing the material. Other methods use special gas environments along with strong magnetic and electric fields. Testing the performance of these barriers is also a challenge, and the most reliable method to measure their efficiency is through the classical technique of testing how well-coated membranes allow gases to pass through.